Hello there, and welcome to Nightfall Science. Tonight, we drift gently beyond our solar system toward exoplanets, distant worlds circling other stars, each one carrying its own quiet story of light, gravity, weather, and time. Let your shoulders ease away from the day, and let your eyes grow heavy whenever they wish. These faraway planets have moved through the dark for billions of years, and they will keep turning softly while you fall asleep. Let's begin. An exoplanet is simply a planet beyond our solar system. The word sounds large, but its meaning is wonderfully calm. Earth is a planet around the Sun. Mars is a planet around the Sun. Jupiter, Saturn, Uranus, and Neptune all belong to the same familiar family. An exoplanet belongs to another star, somewhere beyond the reach of our Sun's warm light. Some exoplanets are giant worlds, broader than Jupiter. Some are small and rocky, closer in size to Earth or Mars. Some move so near their stars that a year lasts only a few days. Others drift much farther away, receiving a faint and patient glow, like a candle seen across a quiet room. The first lesson of exoplanets is that the universe is not built from only one pattern. Our solar system is a beautiful arrangement, but it is not the only possible one. Beyond it, nature has made worlds in many forms. There are planets with thick atmospheres, planets that may have rocky surfaces, planets wrapped in heat, planets locked in cold, and planets moving in places that once seemed unlikely. Many are not seen directly. They are known through hints. A star dims by a tiny amount. A star wobbles with a quiet rhythm. A little starlight passes through a planet's atmosphere and carries a chemical trace back to a telescope. From those gentle clues, whole worlds begin to appear. Across the dark, the galaxy is quietly full of planets. The discovery of 51 Pegasi b opened a new door in astronomy. Before its discovery, many scientists believed other stars probably had planets. The idea felt natural. The Sun had planets, so perhaps other stars did too. But belief is not the same as measurement. Astronomy waits for evidence, and evidence often arrives as something small, repeating, and patient. In 1995, astronomers announced a planet orbiting 51 Pegasi, a star similar to the Sun. The planet is now known as 51 Pegasi b, and also by the name Dimidium. It was the first confirmed exoplanet found around a Sun-like star. The surprise was not only that the planet existed, the surprise was where it was. 51 Pegasi b is a gas giant, broadly similar to Jupiter in type, but it orbits extremely close to its star. It completes one orbit in just over 4 Earth days. In our own solar system, Jupiter is far from the Sun and takes nearly 12 Earth years to complete a single orbit. Around 51 Pegasi, a giant planet moves in a much tighter circle. This kind of planet became known as a hot Jupiter. It changed the way astronomers imagined planetary systems. Giant planets did not always have to remain far from their stars. They could form, migrate, and settle into orbits that seemed strange compared with our own solar system. One discovery became a quiet turning point. A star that looked ordinary had been carrying an unexpected world. Some planets are found when they pass in front of their stars. This is called the transit method. It is one of the most successful ways to find exoplanets. A transit happens when a planet crosses between its star and the telescope watching it. The planet does not block all the starlight. It only dims the star by a very small amount. But if that dip happens again and again, with the same timing, it can reveal a planet in orbit. The image is soft and simple. A star shines steadily. A planet glides across its face. For a short time, the light lowers, like a lamp gently shaded by a passing hand. Then the planet moves on, and the star returns to its usual brightness. From this small fading, scientists can learn many things. The size of the dip can suggest the size of the planet. The timing between dips can reveal the length of the planet's year. If the dips are regular, they trace an orbit. If several patterns overlap, there may be more than one planet moving around the same star. NASA's Kepler mission used this method with great patience. It watched many stars, waiting for these subtle changes. Later, TESS, the Transiting Exoplanet Survey satellite, began scanning much of the sky for nearby stars with possible planets. The transit method is a reminder that discovery does not always arrive loudly. Sometimes a world is found because a distant light becomes slightly softer, again and again, in perfect rhythm. A shadow can be tiny and still carry a planet inside it. Some exoplanets are found by the gentle wobble of a star. This method is called radial velocity, or sometimes the wobble method. It begins with a simple truth about gravity. A planet orbits a star, but the planet also pulls on the star. The star is far more massive, so it does not move very much. Still, it moves a little. The star and the planet circle a shared center of mass. The planet makes a wide motion. The star makes a smaller one. From far away, that tiny stellar motion can sometimes be measured. When the star moves slightly toward Earth, its light shifts a little toward the blue. When it moves slightly away, its light shifts a little toward the red. These changes are extremely small. They are measured with careful instruments called spectrographs, which split starlight into its colors. The planet itself may remain unseen, but the star keeps a rhythm. Its light stretches and compresses in a repeating pattern. That pattern tells astronomers that something is pulling on it. This was the method that revealed 51 Pegasi b. The star showed a regular motion, and the motion matched the tug of a close giant planet. Radial velocity is especially useful because it can help estimate a planet's mass. The transit method can reveal size. Together, size and mass can suggest density. Density hints at whether a planet is rocky, gaseous, icy, or somewhere between. A planet can hide in the glare of its star, but gravity leaves a quiet signature. The galaxy contains many kinds of exoplanets. At first, it is tempting to compare every new world to Earth. Is it like home? Does it have air? Could it have oceans? Could it hold life? These are natural questions, but exoplanets invite a wider kind of wonder. Some exoplanets are gas giants, like Jupiter or Saturn. They may have no solid surface that a person could stand on. Their atmospheres can be deep and layered, with clouds, winds, and chemistry shaped by heat and pressure. Some are Neptune-like worlds. They may have thick atmospheres and icy or rocky interiors. Some are smaller than Neptune but larger than Earth. These are often called mini-Neptunes, and they are common in the galaxy. Even though our own solar system does not have one, some are called super-Earths. This does not mean they are better than Earth. It only means they are more massive than Earth, but still smaller than Neptune. They may be rocky, some may have atmospheres, some may be very hot, others may be colder and calmer. Some exoplanets are terrestrial, meaning they are rocky like Earth, Mars, Venus, or Mercury. These worlds interest scientists deeply, especially when they orbit at distances where surface temperatures could allow liquid water under the right conditions. The names are categories, not complete stories. A gas giant can be close or far. A super-Earth can be dry, ocean-covered, or wrapped in thick air. A rocky world can be gentle or harsh, depending on its star, atmosphere, orbit, and history. Each planet type is like a different instrument in the same quiet orchestra. Together, they show how many ways a world can be made. TRAPPIST-1 is a small star with 7 Earth-sized planets. It lies about 40 light-years away, in the direction of the constellation Aquarius. The star itself is not like the Sun. It is much smaller, cooler, and dimmer. It is an ultra-cool red dwarf, a type of star that burns with a softer, redder light. Around this small star moves a remarkable family of 7 planets. All are close to Earth in size. They orbit much nearer to their star than Earth orbits the Sun. But because TRAPPIST-1 is so cool and faint, closeness there does not mean the same thing it would mean near our Sun. Several of the planets lie in or near the star's habitable zone. This phrase is often misunderstood. It does not mean the planets are inhabited. It does not even prove they have water. It means that, with the right atmosphere, temperatures could allow liquid water to exist on a planet's surface. The beauty of TRAPPIST-1 is partly in its rhythm. The planets are packed close together. Their orbits are linked by gravity. They tug on one another in measurable ways, like bells ringing in a pattern too slow for ears but clear to mathematics. Because these planets pass in front of their star, telescopes can study them with the transit method. Future and current observations can look for signs of atmospheres, or for the absence of thick air. TRAPPIST-1 does not need to be turned into a promise. Its real nature is already enough. 7 small worlds move around a dim red star, each one keeping time with the others. In a compact system far away, gravity plays a gentle song. The habitable zone is a quiet band of possibility. It is sometimes called the Goldilocks zone. This is the region around a star where a planet could have temperatures suitable for liquid water on its surface, if the planet also has the right atmosphere. Too close to the star, water may be lost to heat. Too far away, it may freeze. In between, there may be a gentler range. But the habitable zone is not a guarantee. Venus and Mars help show this clearly. Venus is near the inner region of the Sun's habitable zone, but its thick atmosphere traps heat strongly. Mars is near the outer region, but its atmosphere is thin and cold. Earth is habitable not only because of its distance from the Sun, but because of its atmosphere. magnetic history, water, geology, and many other details. For exoplanets, the habitable zone is a first clue. It narrows the search. It says, here is a place where water might be possible. But many other questions remain. Does the planet have an atmosphere? Is it rocky? Is there enough pressure for liquid water? Has the star been calm enough over time? Does the planet rotate freely, or is one side always facing the star? Different stars have different habitable zones. Around a bright star, the zone is farther out. Around a cool red dwarf, it is much closer in. A planet can orbit near a red dwarf and still receive only modest warmth. The habitable zone is not a destination, it is a doorway. Beyond it, the deeper story of each world begins. Kepler 186f showed that Earth-sized planets can exist in habitable zones. This planet was discovered using NASA's Kepler Space Telescope. It orbits a star smaller and cooler than the Sun. It belongs to a system with several known planets, but Kepler 186f became especially important because of its size and orbit. It was the first validated Earth-sized planet found in the habitable zone of another star. That phrase is careful and important. Earth-sized means its diameter is close to Earth's. It does not mean it has oceans, clouds, forests, or a breathable sky. Habitable zone means liquid water could be possible under the right conditions. It does not mean water has been found there. Still, the discovery was a meaningful step. It showed that planets near Earth size are not limited to our solar system. They can exist around other stars, in regions where sunlight is not too intense and not too faint. Kepler 186f receives light from a star redder and cooler than the Sun. If someone could imagine standing there, the daylight might not resemble Earth's golden noon. It could be softer and redder. Shadows might feel different. The color of a sky, if there is a sky, would depend on the air. The color of any surface would depend on minerals, frost, dust, or clouds. Science does not need to fill in what is unknown. It can rest in what has been measured. A small planet crosses its star. The starlight dips. The orbit is calculated. The size is estimated. And a new possibility joins the map. Far away, an Earth-sized world moves in a quiet zone of red light. WASP 76b is a world where iron may fall like rain. It is a gas giant exoplanet, larger than Jupiter, orbiting very close to its star. Its year lasts less than 2 Earth days. The planet receives intense radiation, and it is likely tidally locked. That means one side faces the star in permanent day, while the other side remains in permanent night. On the day side, temperatures are high enough for metals such as iron to become vapor. In that fierce heat, iron is no longer the hard material familiar from tools, bridges, or stone-colored meteorites. It becomes part of the atmosphere. Winds can carry that vapor toward the cooler night side. As the air cools, iron may condense into droplets. The result is an extraordinary kind of weather. Rain made not of water, but of metal. This idea sounds strange, yet it follows the same broad pattern as weather on Earth. Heat lifts material, air carries it, cooling changes it. Clouds form when conditions allow. Rain falls when droplets gather enough weight. The ingredients are different. The temperatures are different. The sky is not Earth's sky, but the process is still a kind of planetary breathing, shaped by light, wind, chemistry, and motion. WASP 76b is not gentle in any human sense. It is not a place for footsteps. But from far away, it becomes a peaceful lesson in possibility. Even iron, so solid in human hands, can become part of clouds under another sun. A planet can teach that weather is not one thing. It is matter finding its rhythm beneath starlight. Kelt 9b is hotter than many stars. This planet is an ultra-hot Jupiter. It orbits a bright hot star called Kelt 9, about 670 light-years away. Its orbit is extremely tight, and its year lasts only about 1.5 Earth days. The day side of Kelt 9b is so hot that molecules can be torn apart. In cooler regions, atoms may come together again. The atmosphere becomes a place where chemistry is constantly being undone and remade by heat and radiation. This world shows how strongly a star can shape a planet. In our own solar system, the sun warms Earth, drives weather, lights the oceans, and helps sustain life. Around Kelt 9, starlight is far more intense. The planet does not simply receive warmth, it is sculpted by energy. A useful image is a snowflake near a flame. Too close, and the delicate structure cannot remain. On Kelt 9b, Some molecules cannot keep their shapes on the day side. They separate, move, and later recombine where temperatures ease. The planet is a reminder that the word planet covers an enormous range. Earth is a planet. Jupiter is a planet. Kelty 9b is also a planet, though its atmosphere behaves in ways that feel almost star-like. Even the most extreme worlds belong to the same large family of objects orbiting stars. Around a brilliant sun, Kelty 9b glows as a world almost made of heat. Some exoplanets orbit 2 stars. These are called circumbinary planets. Instead of circling one star, they orbit a pair of stars that also orbit each other. The idea once sounded like science fiction, but real examples have been found. A planet can move around 2 suns and keep a stable path. One known example is Kepler 16b. It is a cold gas giant, not a second Earth. But its existence is important because it shows that planets can form and survive in binary star systems. A binary star system is a pair of stars bound by gravity. They circle their shared center of mass, sometimes close together and sometimes farther apart. Around some pairs, a disk of gas and dust can surround both stars. Inside that disk, particles can gather, tiny grains become larger bodies. Larger bodies grow into planets. From the surface of a circumbinary world, if it had a surface, the sky would have rhythms unlike Earth's. There could be 2 suns rising and setting. One might be brighter, one might be dimmer. Their positions would change as they moved around each other. Shadows could shift in ways that feel unfamiliar and graceful. The seasons might be shaped by the planet's orbit and by the changing dance of the stars inside it. Daylight could arrive with more than one color. Sunset could be a layered event, with one sun lowering while another still glows. The universe does not insist that every planet have one sun. Some worlds are born into double light. In such systems, even daylight becomes a duet. Some planets may wander without any star at all. These are often called rogue planets, or free-floating planets. They are planetary mass worlds moving through space, without being bound to a star. Some may have formed around stars and later been pushed out by gravitational encounters. Others may have formed more like tiny failed stars, from collapsing clouds of gas and dust. A rogue planet does not have a sunrise in the usual sense. It does not have a year measured around a nearby star. No warm disk of daylight crosses its sky. It travels through interstellar space, under the distant glow of the galaxy. This can sound lonely, but in a calm view it becomes another form of stillness. A rogue planet is not lost. It is following gravity on a larger scale. It belongs not to one star system, but to the Milky Way itself. Scientists can search for such worlds through microlensing. When a dark object passes in front of a more distant star, its gravity can bend and brighten the background starlight for a short time. The planet may remain invisible, but its gravity briefly acts like a natural lens. For a little while, a wandering world changes the light from something far behind it. Then the alignment passes, and the world continues through the dark. No sunrise follows it, only the quiet galaxy and the long patience of gravity. The atmospheres of exoplanets can be studied through filtered starlight. This technique is called transmission spectroscopy. It is one of the most delicate tools in exoplanet science. When a planet passes in front of its star, a small amount of starlight travels through the planet's atmosphere before reaching a telescope. Atoms and molecules in that atmosphere absorb certain wavelengths of light. They leave patterns behind, like soft fingerprints in a rainbow. By studying those patterns, scientists can search for gases such as water vapor, carbon dioxide, methane, sodium, or other atmospheric ingredients, depending on the planet and the instrument. The planet itself may be too far away to see as a disk, but during a transit, its atmosphere forms a thin ring around its dark silhouette. That ring is tiny compared with the star. Its signal is faint. It must be separated carefully from the star's own behavior and from the noise of measurement. The James Webb Space Telescope is especially useful for this work because it observes infrared light with great sensitivity. Infrared light can reveal molecules that are difficult to study in visible wavelengths. The idea is wonderfully quiet. A planet crosses a star. A little starlight passes through air. That light travels across many trillions of miles. A telescope gathers it. A spectrum appears. And in the spectrum, chemistry whispers. The atmosphere of a distant world is not brought home in a bottle. It arrives as a pattern of missing colors. Exoplanets remind us that the night sky is not empty. To the unaided eye, Stars look like points of light. They seem single and still, scattered across the dark. But around many of them, planets may be moving. Some are close to their stars. Some are far away. Some are hot giants. Some are small rocky worlds. Some travel in families. Some may wander alone. Most of these planets cannot be seen directly. They are too faint beside their stars. A star can outshine its planet by an enormous amount, the way a lighthouse can hide a firefly beside it. Yet the planets are there. They tug, they transit, they bend light, they warm and cool, they carry atmospheres, clouds, rocks, gases, or unknown surfaces. The discovery of exoplanets changes the feeling of looking upward. The stars are no longer only stars. They are possible suns for other worlds. Each point of light may have a hidden architecture around it, a system of orbits, shadows, and quiet weather. This does not make Earth less special. It makes Earth more precious. Home becomes one world among many, but still the only one known to hold oceans, forests, birds, cities, memory, and sleep. The universe is wide, but it is not barren. It is rich with structure. It makes stars, and around stars it often makes planets. It gathers dust into worlds and sets those worlds turning. In the dark between the stars, there is more than distance. There is possibility, moving softly in orbit. Super-Earths are worlds larger than Earth, but smaller than Neptune. The name can sound dramatic, but it is only a size and mass category. A super-Earth is not necessarily a better Earth, or a more living Earth, or a planet with blue oceans and green continents. It is simply a planet more massive than Earth, but lighter than ice giants such as Neptune and Uranus. This category is one of the great surprises of exoplanet science. The solar system has small rocky planets like Earth and Mars. It has giant planets like Jupiter and Saturn. It has ice giants like Uranus and Neptune. But it does not have anything between Earth and Neptune. Around other stars, these middle-sized planets are common. Some super-Earths may be rocky. Some may be wrapped in thick atmospheres. Some may have deep oceans. Some may be dry, hot, and dense. A planet's size gives an important clue, but it does not tell the whole story. A super-Earth close to its star may be baked by heat. One farther out may be cold and dim. One with a thick atmosphere may trap warmth strongly. One without much air may have a bare and silent surface. Two planets can share a size category and still be completely different worlds. The category is useful because it gives astronomers a first way to sort many discoveries. It is like placing stones, shells, and glass beads into broad bowls before studying each one more closely. Super-Earths remind astronomy that the solar system is not a complete catalogue. Between familiar Earth and distant Neptune, the galaxy has made many quiet in-between worlds. Mini-Neptunes are common, even though our solar system has none. A mini-Neptune is smaller than Neptune, but larger than Earth. These planets often appear in exoplanet surveys. They may have rocky or icy cores surrounded by thick envelopes of gas, usually hydrogen and helium. Some may be more like small gas-rich worlds. Others may sit close to the boundary between rocky planets and gaseous planets. Their commonness is one of the soft surprises of modern astronomy. A person could grow up learning the solar system and imagine it as a standard pattern: small rocky worlds near the star, gas and ice giants farther away. But other stars show different arrangements. They often have planets in sizes that our own system skipped. Mini-Neptunes are difficult to imagine because there is no local example to visit with spacecraft. Neptune itself gives a clue, with its blue color, deep atmosphere, and cold outer orbit. But mini-Neptunes can orbit much closer to their stars. Their atmospheres may be warmer, puffier, or shaped by radiation in unfamiliar ways. Some mini-Neptunes may slowly lose their atmospheres, especially if they orbit near active stars. As the outer gas escapes, they may leave behind denser cores. This process can help explain gaps in the sizes of exoplanets, where some planets seem to fall into different families. A mini-Neptune may not have a surface in the ordinary sense. Falling inward through its atmosphere might mean passing through thicker and thicker layers of gas until pressure and heat become immense. These planets are quiet reminders that nature fills the spaces between categories. Where the solar system leaves a gap, the galaxy places many worlds. Proxima Centauri b is the closest known exoplanet to Earth. It orbits Proxima Centauri, the nearest star to the Sun. The system sits about 4 light-years away. That is close in cosmic terms, but still enormously distant in human terms. Light itself takes more than 4 years to cross the gap. A spacecraft traveling with today's ordinary technology would need far longer. Proxima Centauri is a red dwarf star. It is smaller, cooler, and dimmer than the Sun. Its planet, Proxima Centauri b, orbits very close to it, completing 1 year in about 11 Earth days. Because the star is faint, the planet can orbit close and still receive an amount of energy that places it in the broad conversation about habitability. But the word possible must remain gentle and careful. Proxima Centauri b has not been seen crossing in front of its star from Earth's viewpoint. That means the usual transit method cannot easily reveal its radius or atmosphere. Scientists know it mostly through the radial velocity method, by the tiny tug it gives its star. The star itself is active and can produce strong flares. Such flares may affect any atmosphere the planet might have. Models are needed to explore whether air could survive and under what conditions. Still, Proxima Centauri b carries a special feeling. It is not the most Earth-like world known. It is not a confirmed home for life. Its meaning is simpler. The nearest star to the Sun has at least one planet. The closest neighboring star is not alone. It has a world moving beside it in red light. A planet's year can last only a few days. On Earth, a year feels long because it is woven into seasons, birthdays, migrations, school years, harvests, and memory. It takes about 365 days for Earth to orbit the Sun, but around other stars, some planets complete an orbit in far less time. Hot Jupiters often have very short years. They move close to their stars, circling quickly under strong gravity. Some complete an orbit in only a few days. Ultra-short period planets can move even faster, with years measured in hours. This does not mean time itself changes on those worlds. It means the path around the star is small, and the orbital speed is high. A planet close to its star must move quickly to stay in orbit. The closer the orbit, the shorter the year tends to be. A short year changes the meaning of a planet's environment. Starlight is often intense. Tides can be strong. The planet may become tidally locked, with one side facing the star and the other turned away. Weather patterns may wrap around the globe in unusual ways. The idea can be held softly. Somewhere, a planet completes a whole year while one Earth weekend passes. Another may circle its star before a night on Earth has ended. In the telescope data, this appears as frequent dips in light, repeating with calm precision. A year is not one universal length. It is the rhythm each planet keeps with its own star. Some planets may be tidally locked, with one side always facing their star. Tidal locking happens when gravity gradually synchronizes a world's rotation with its orbit. The Moon is tidally locked to Earth. That is why the same lunar face is always turned toward us. Many close-in exoplanets may be similarly locked to their stars. On a tidally locked planet, one hemisphere receives constant daylight, the other remains in long continuous night. Between them lies a boundary region, often called the terminator, where the star may hang near the horizon. There, depending on the atmosphere, conditions might be more moderate than at the hottest or coldest regions. For planets close to small red dwarf stars, tidal locking may be common. This once seemed like a simple problem for habitability. A permanent day side could be too hot. A permanent night side could be too cold. But atmosphere changes the story. If a planet has enough air, winds can carry heat from day to night. Oceans, if present, can also move warmth. The planet becomes a world of circulation. Air rises beneath the endless sun, flows outward, cools, sinks, and returns. Clouds may gather on the day side. The night side may hold ice, or it may remain warmer than expected if the atmosphere is thick. Tidal locking is not automatically a barrier to calm conditions. It is a different arrangement of light and motion. On such a world, sunrise may never come to one place, and sunset may never leave another. The sky becomes still, while the atmosphere keeps moving. Kepler 22b was one of the first famous habitable zone discoveries. It orbits a sun-like star, though slightly smaller and cooler than the Sun. Its orbit places it in the habitable zone, where liquid water could be possible under the right atmospheric conditions. NASA announced its discovery in 2011, and it quickly became one of the most widely recognized exoplanets. Kepler 22b is larger than Earth, about 2.1 times Earth's radius. That size leaves room for several possibilities. It could be a rocky planet with a thick atmosphere. It could be a water-rich world. It could be more gaseous than Earth. Its true nature is not fully known. This is a common pattern in exoplanet science. A discovery can be important even when many details remain uncertain. Kepler 22b helped show that planets in habitable zones are not rare curiosities. The Kepler mission was beginning to reveal that worlds at promising distances from stars could be found. A planet's radius gives only part of the story. Mass is needed to estimate density. Atmosphere is needed to understand surface conditions. Clouds, greenhouse gases, reflectivity, and geology can all shape temperature. Habitability is never a single measurement. Still, Kepler 22b has a gentle place in the history of discovery. It expanded the sense of what Kepler was finding. It made distant habitable zone planets feel less like speculation and more like a growing field of study. A faint dip in a star's light became a quiet landmark. It showed that possible ocean worlds may wait far beyond the Sun. Some exoplanets may be ocean worlds. An ocean world is a planet that may hold large amounts of water. In some cases, water could cover much or all of the surface. In others, water might exist beneath ice or deep under thick layers of atmosphere. Around other stars, the possibilities spread widely. The idea begins with familiar places. Earth is an ocean world in one sense, with seas covering most of its surface. In the outer solar system, moons such as Europa and Enceladus may have global oceans beneath icy crusts. These local examples show that water can be stored in different ways, under different conditions. For exoplanets, size and density can offer clues. If a planet is larger than Earth but less dense than solid rock, it may contain water, gas, or a mixture of both. But the answer is not simple. A thick hydrogen-rich atmosphere can make a planet appear larger. A deep ocean under high pressure can create exotic forms of ice. Clouds can hide what lies beneath. An ocean world around another star may not look like Earth. Its sea could be deeper than any earthly ocean. Its atmosphere could be heavy. Its sky could be dimmer or redder. Its water could be locked under ice or warmed by internal heat rather than sunlight. The phrase ocean world is therefore not a picture, but a doorway into several possible interiors. Water is a simple molecule, but worlds can hold it in many quiet ways. Lava worlds may have molten surfaces under extreme starlight. Some rocky exoplanets orbit so close to their stars that their surfaces may melt. These are sometimes called lava worlds. They are often small, dense planets with very short orbital periods. Because they receive intense heat, rock itself may become liquid on the day side. On Earth, lava appears during volcanic eruptions. It glows, flows, cools, and becomes stone again. On a lava world, molten rock could cover vast regions, perhaps forming a magma ocean beneath a star that never sets. The atmosphere, if one exists, may contain vaporized rock and minerals. A planet like this shows that rock is not always solid in planetary science. Under enough heat, silicates can melt. Under stronger conditions, they can evaporate. The boundary between ground and sky can become more complicated, with minerals moving through heat, vapor, and condensation. If the planet is tidally locked, one side may be far hotter than the other. The day side could glow with molten material. The night side might be cooler and darker, perhaps allowing minerals to condense. Winds, if present, could carry vapor from one side to another. This is not a world of gentle landscapes, but it is still part of the calm variety of planets. It shows how the same ingredients found in familiar rocks can behave differently under another star. Stone, like water and iron, has its own weather when the heat is high enough. Even the ground can become a slow, glowing sea. Puffy planets are giant worlds with surprisingly low density. Some exoplanets are larger than Jupiter, but much less massive than expected. Their atmospheres are stretched outward, making them appear inflated. These worlds are sometimes called puffy planets, or hot Saturns, depending on their properties. WASP-39b is one famous example, often studied by the James Webb Space Telescope. It is a hot gas giant with a large diameter and relatively low mass compared with Jupiter. Its atmosphere is extended and warm, making it an excellent target for spectroscopy. A puffy planet is not puffy like a cloud one could touch. It is a giant world whose outer layers are spread over a large volume. Heat from the nearby star can help inflate the atmosphere. Internal processes may also play a role. The result is a planet with a broad silhouette when it transits its star. This broad atmosphere is scientifically useful. When starlight passes through it during a transit, gases can leave stronger signatures. That makes puffy planets especially good for atmospheric study. Webb observations of WASP-39b have revealed molecules including carbon dioxide and other chemical features, helping scientists test models of planetary atmospheres. The planet becomes a kind of natural lantern shade. Light from the star filters through its gas. The atmosphere writes chemistry into the spectrum. Telescopes receive the message. A low-density giant may seem delicate, though it is enormous. In its swollen atmosphere, distant light finds room to speak. WASP-39b helped Webb reveal the chemistry of a distant atmosphere. The James Webb Space Telescope brought new sensitivity to exoplanet studies, especially in infrared light. One of its early major targets was WASP-39b, a hot, puffy gas giant orbiting a sun-like star. Because the planet has a large atmosphere and transits its star, it offers a strong signal for transmission spectroscopy. When WASP-39b passes in front of its star, some starlight filters through the planet's atmosphere. Molecules in the gas absorb specific wavelengths. Webb can measure these patterns with great care. In observations of WASP-39b, scientists detected carbon dioxide clearly in an exoplanet atmosphere. Later studies revealed a richer chemical picture, including evidence of sulfur dioxide produced by photochemistry. Photochemistry means chemistry driven by light. On Earth, sunlight helps drive chemical reactions in the atmosphere. Around WASP-39b, starlight also shapes the chemistry of the air. This is important because atmospheres are more than lists of gases. They are active systems. Light, heat, winds, and molecules interact. A planet's air changes with its star, its temperature, and its history. WASP-39b is not a habitable world. It is too hot and too gaseous for that familiar idea. Yet it is deeply valuable. It shows that telescopes can read the atmospheres of planets many light years away. The atmosphere of a distant giant becomes a page written in infrared light. Webb does not bring the planet closer. It lets the planet's chemistry arrive more clearly. Direct imaging lets astronomers photograph a few exoplanets. Most exoplanets are not seen directly. They are found by their effects on stars. They dim starlight during transits. They tug stars into tiny wobbles. They bend background light through gravity. But in a small number of cases, planets can be imaged. Direct imaging is difficult because stars are bright and planets are faint. A star can outshine its planet by millions or billions of times. Seeing a planet near a star is like trying to notice a firefly beside a spotlight from very far away. Astronomers use special instruments to block the star's light. These tools are called coronagraphs, or star shades in different designs. Adaptive optics can also help, correcting for the blur of Earth's atmosphere when observations are made from the ground. Direct imaging works best for young, massive planets far from their stars. Young giant planets still glow with leftover heat from formation, especially in infrared light. If they orbit far enough from the star, they are easier to separate from the glare. One famous directly imaged system is HR 8799, which has multiple giant planets orbiting far from a young star. Over years of observations, astronomers can actually see the planets shift in their orbits. The motion is slow, but real. The images are not like close-up photographs from a spacecraft. The planets appear as small points of light, yet those points are precious. They are worlds seen directly, not only inferred. A tiny dot beside a hidden star can hold the warmth of a young planet. Microlensing can reveal planets by the way gravity bends light. Gravity does not only pull on matter, it also bends the path of light. When a foreground star passes in front of a more distant background star, its gravity can act like a lens, briefly magnifying the background light. If the foreground star has a planet, the planet can add a smaller extra brightening. This method is called gravitational microlensing. It is especially useful for finding planets at wider orbits, and sometimes for detecting planets that may be hard to find by transits or radial velocity. It can also reveal free-floating planet candidates if the lensing object is not clearly tied to a star. The event does not repeat in the usual way. A transit can happen again every orbit. A radial velocity signal can continue for years, but a microlensing alignment is usually a one-time moment. The stars move, the alignment happens, the light brightens, and then the arrangement passes. This gives microlensing a quiet beauty. It depends on chance alignments across enormous distances. A planet may reveal itself not by shining, not by blocking light, and not by tugging a visible star in a repeated rhythm, but by briefly shaping the path of light from something behind it. For a short time, gravity becomes a lens made of space itself. Then the lens moves on, and the sky returns to its earlier brightness. Some planets are found through timing. In some systems, a planet's presence can be detected because it changes the timing of another object. This can happen in several ways. For example, if a transiting planet is pulled by another planet, its transits may arrive a little early or a little late. These are called transit timing variations. The idea is like listening to a clock that almost keeps perfect time. If the ticking shifts slightly, something may be disturbing it. In a planetary system, gravity provides the disturbance. Neighboring planets tug on each other. Their orbits are not isolated. Each one gently adjusts the others. Transit timing variations have been especially helpful for systems with multiple planets. They can reveal masses, orbital relationships, and sometimes planets that do not transit at all. The method shows that planetary systems are not just collections of separate worlds. They are connected structures. Timing also matters for pulsar planets, some of the earliest confirmed exoplanets. Pulsars are dense stellar remnants that emit regular pulses of radiation. If planets orbit a pulsar, their gravity can shift the timing of those pulses. In the early 1990s, planets were found around a pulsar, before 51 Pegasi b was discovered around a sun-like star. These were strange first worlds, orbiting the remains of a star rather than a warm, living sun. They showed that planets can exist in unexpected places. A planet does not always announce itself with light. Sometimes it is found in the smallest change of a cosmic clock. The first confirmed exoplanets orbited a pulsar. Before astronomers confirmed 51 Pegasi b around a sun-like star, planets were discovered around the pulsar PSR B127. A pulsar is the dense remnant of a massive star that ended its life as a supernova. It spins rapidly and sends beams of radiation into space. If those beams sweep across Earth, they arrive as regular pulses. The pulses can be timed with extraordinary precision. When planets orbit the pulsar, their gravity causes tiny changes in the arrival times of the pulses. From those changes, astronomers inferred the presence of planets. These worlds are very different from the gentle image often attached to exoplanets. They do not orbit a normal star like the Sun. They circle a stellar remnant. Their system has passed through a violent history. Yet the discovery is part of the same calm truth. Planets can exist in many environments. The pulsar planets expanded the definition of where to look. They showed that planet formation, or planet survival, can take place under conditions far from familiar. A system can be transformed by stellar death and still hold orbiting worlds. For sleep science, the wonder is in the precision. A rotating remnant sends pulses across space. Those pulses arrive like a clock. Slight changes reveal small companions circling in the dark. The first confirmed exoplanets were not found around a sun-like star. They were discovered by listening to time itself. Red dwarf stars may host many small planets. Red dwarfs are the most common type of star in the Milky Way. They are smaller, cooler, and dimmer than the Sun. Because they are so common, they are important in the search for exoplanets. If many red dwarfs have planets, then a large fraction of the galaxy's worlds may orbit these faint stars. A red dwarf's habitable zone lies close in, because the star gives off less light. Planets in that zone may have short years. They may also become tidally locked. Their stars can be active, especially when young, producing flares that affect atmospheres. This creates a careful balance in the study of red dwarf planets. On one hand, small planets around small stars are easier to find by the transit method. When an Earth-sized planet crosses a red dwarf, it blocks a larger fraction of the star's light than it would around a sun-like star. That makes the signal stronger. On the other hand, stellar activity can be challenging for atmospheres and for observations. Flares, star spots, and changing brightness can complicate the interpretation of data. Still, red dwarfs are too important to ignore. TRAPPIST-1, Proxima Centauri, and many other systems show that small stars can host fascinating planets. These stars burn their fuel slowly and can last for extremely long times, far longer than stars like the Sun. Around the galaxy's smallest common stars, planets may be quietly abundant. Dim red suns may carry some of the Milky Way's longest stories. K-type stars may be gentle places to search. K-type stars are sometimes called orange dwarfs. They are smaller and cooler than the Sun, but larger and warmer than red dwarfs. They can live longer than sun-like stars, while often being calmer than many red dwarfs. This makes them interesting in the search for potentially habitable planets. A K-type star gives steady light over long timescales. Its habitable zone is closer than the Sun's, but not as close as the tight zones around cool red dwarfs. Planets there may avoid some of the challenges of orbiting very active small stars. Kepler 442b is one example of a planet around a K-type star. It is classified as a super-Earth and orbits in a region often discussed in relation to habitability. Its year lasts about 112 Earth days. Like many distant worlds, it is known mostly through indirect measurements, and many details remain uncertain. K-type stars invite a quiet kind of attention. They are not as bright as the Sun. They are not as numerous as red dwarfs. They sit between categories, offering long lifetimes and moderate light. In the search for life beyond Earth, stability matters. Atmospheres need time. Oceans, if present, need time. Chemistry needs time. Worlds change slowly, and stars that shine steadily for billions of years may offer calm conditions for long planetary histories. An orange star can be less famous than a yellow sun, but in its steady light, a planet may have time to become complex. Exoplanet science is built from patience. No telescope has flown to these worlds. No spacecraft has crossed the light years between stars and sent back close photographs of an exoplanet's surface. Most of what is known comes from light, gravity, and time. A planet passes in front of a star. A star moves slightly under a planet's pull. A distant beam brightens because gravity bends it. A spectrum shows that certain colors are missing. A transit arrives a little late because another planet has tugged the orbit. Each clue is small. Each clue must be checked. Signals can be confused by star spots, stellar activity, instrument noise, background stars, or assumptions in the model. Scientists compare methods, repeat observations, and wait for patterns. This patience is part of the beauty. Exoplanet science is not only about strange worlds, it is about learning how to know something very far away. It is about turning tiny changes into reliable understanding. A graph becomes a planet's size. A wobble becomes a map. A spectrum becomes an atmosphere. A repeated shadow becomes a year. A timing shift becomes a hidden neighbor. The process is careful, but the result is vast. Thousands of planets have joined the catalog, and many more candidates wait for confirmation. Each one began as a small signal in the light. Far away, planets move without needing to be seen. Here, patient minds learn to recognize their quiet traces. Proxima Centauri is small, dim, and very close to the Sun. In the deep scale of the galaxy, close still means far. Proxima Centauri is the nearest known star to our solar system, but its light takes more than 4 years to reach Earth. It is part of the Alpha Centauri system, a famous neighboring group of stars in the southern sky. Proxima itself is a red dwarf. It is far smaller and cooler than the Sun. If the Sun is imagined as a steady golden lamp, Proxima is more like a small red coal, glowing with less light, but lasting for a very long time. Around this faint star moves Proxima Centauri b, a planet discovered through the radial velocity method. The planet's gravity tugs gently on the star, creating a measurable wobble. From that wobble, scientists estimate that the planet is at least a little more massive than Earth. Its orbit is short. A year on Proxima Centauri b lasts only about 11 Earth days. Yet because the star is so dim, this close orbit places the planet in a region where the amount of received energy is interesting to scientists studying habitability. Still, many questions remain. The planet may be tidally locked. The star can flare. Its atmosphere, if it has one, is unknown. Its surface is unknown. Its weather is unknown. This is part of the quiet discipline of exoplanet science. It holds wonder without pretending certainty. A nearby star has a planet. That planet may be rocky. It receives a meaningful amount of red starlight. Beyond that, patience is needed. The nearest stellar neighbor is not empty. A small world moves there, softly hidden in the pull of gravity. 2I 700 is a red dwarf, with small planets in gentle orbits. The name 2I means TESS object of interest. It comes from NASA's Transiting Exoplanet Survey satellite, which searches for planets by watching stars dim during transits. 2I 700 is a small, cool star, a little over 100 light-years away. Around it, TESS found multiple planets. Two of these worlds, 2I-700d and 2I-700e, have drawn special interest because they are Earth-sized or near-Earth-sized and orbit in the star's habitable zone. This does not mean they are Earth twins. It does not mean they have oceans. It means that, with a suitable atmosphere, their distance from the star could allow surface liquid water. 2I-700e is especially gentle in scale. NASA's catalog lists it as a terrestrial exoplanet with a radius slightly smaller than Earth's and an orbital period of about 27.8 days. Its star is cooler and dimmer than the Sun, so a short orbit can still place the planet in a temperate region. A system like TOI-700 shows why TESS is so valuable. Instead of staring at only one small patch of sky, TESS surveys broad regions, looking for planets around nearby bright stars. Nearby in astronomy means easier follow-up. It means future telescopes may study these systems in more detail. The planets of TOI-700 are not places that can be described like visited worlds. They remain distant, measured by starlight and careful models. But in their repeating shadows, the telescope finds calm possibility. LHS-140b is a dense super-Earth in a habitable zone orbit. LHS-140 is a small red dwarf star. Around it moves LHS-140b, a planet discovered by the transit method. NASA's catalog describes it as a super-Earth, with a mass several times Earth's and a radius less than twice Earth's. Its orbit takes about 24.7 Earth days. Because its star is cool and dim, that relatively close orbit places the planet in a region of interest for habitability studies. Again, this must be said carefully. The habitable zone is not a promise, it is a starting point. A planet also needs the right atmosphere, pressure, chemistry, and history for surface liquid water. LHS-140b is interesting because its size and mass suggest it may be a rocky world, though details continue to be studied. A dense planet is different from a puffy one. Density hints that much of the planet's material is heavier than gas, perhaps rock and metal. A transiting planet like this gives astronomers repeated chances to observe. Every time it crosses its star, it offers a small opportunity to study its size and, perhaps, its atmosphere. If air is present, starlight passing around the planet's edge may carry tiny chemical signs. The star itself is much less luminous than the Sun. The planet's sky, if it has one, would be lit by redder light. Its year would pass in less than one Earth month. Its seasons, if any, would depend on its orbit, tilt, atmosphere, and rotation. A small red star shines quietly. Around it, a heavy world keeps a steady, measured path. GJ-1214b is a mini Neptune wrapped in haze. This planet orbits a red dwarf star about 48 light-years from Earth. It is larger than Earth but smaller than Neptune, placing it among the sub-Neptune or mini-Neptune worlds that are common in the galaxy. It has been studied many times because it transits its star and is relatively nearby by astronomical standards. For years, GJ-1214b puzzled scientists because its spectrum appeared mostly flat. That means the expected chemical features were muted. One explanation is clouds or haze high in the atmosphere, blocking a clearer view of deeper layers. NASA has described GJ-1214b as likely having a steamy, hazy atmosphere. Webb observations have helped scientists study the planet's heat and atmospheric behavior in more detail. It is not a world like Earth. It may have a thick envelope and conditions far removed from anything familiar at the surface. Yet GJ-1214b is valuable because it represents a common class of planet. Mini-Neptunes and sub-Neptunes appear often around other stars. Understanding one nearby example can help astronomers interpret many others. The haze itself is a kind of lesson. Atmospheres do not always reveal themselves easily. Sometimes clouds hide the chemistry below. Sometimes aerosols scatter light. Sometimes a planet's air becomes a veil, softening the signatures that telescopes are trying to read. A mini-Neptune can be both common and mysterious. Behind a quiet haze, a distant atmosphere keeps its secrets gently. HD 2009-458b was the first transiting exoplanet found around a Sun-like star. It is also nicknamed Osiris. This hot Jupiter orbits very close to its star, completing a circuit in only a few days. It became famous because it crossed in front of its star from Earth's viewpoint, making it the first exoplanet detected by the transit method after first being found through radial velocity. This was a beautiful moment for exoplanet science. One method found the planet through the star's wobble, Another confirmed its passage across the star's face. Together, the measurements gave both mass and size, allowing scientists to estimate its density. HD 2009-458b also became the first exoplanet whose atmosphere was detected. Later observations showed that hydrogen was escaping from the planet into space. NASA and ESA described an extended envelope of escaping gas, shaped by the strong radiation of the nearby star. The image is almost comet-like. A giant planet orbits close to its sun. Its upper atmosphere heats and expands. Some gas rises beyond the planet's grip and trails away. The planet is not a solid stone losing a few grains of dust. It is a vast gaseous world, slowly giving part of itself back to space. This does not happen quickly in human terms. The planet remains enormous, but the process reveals how stars can reshape planets over time. Atmospheres are not always permanent. Around a close star, even a giant world can breathe material into the dark. Some exoplanet atmospheres slowly escape into space. Atmospheric escape is a natural process. It can happen when gas at the top of an atmosphere gains enough energy to overcome gravity. On Earth, a small amount of hydrogen and helium can escape. On close-in exoplanets, the process can become much stronger. A star gives off light, heat, and high-energy radiation. For planets orbiting very close, this energy can warm the upper atmosphere until it expands. If the planet's gravity is not strong enough to hold all of that gas, some of it flows away. This process may be important for understanding why planets come in different sizes. Some mini-Neptunes close to their stars may lose thick hydrogen and helium envelopes over time. What remains could be a smaller, denser core. In this way, a planet's history can be written not only by formation, but by erosion from starlight. Atmospheric escape is measured through careful observations. During a transit, escaping hydrogen or other gases can absorb certain wavelengths, making the planet seem larger in those colors. The atmosphere extends beyond the visible body of the planet, like a thin veil moving outward. The idea is slow and graceful from a distance. A planet receives light. Its upper air warms, gas expands, lifts and drifts away. Over millions or billions of years, that gentle loss may change the world. Planets are not fixed objects. They are shaped by time, gravity, and the quiet pressure of stars. Planet migration explains why giant worlds can orbit so close to stars. In the older picture drawn from the solar system, giant planets belonged far from the Sun. Jupiter and Saturn are cold outer worlds. They formed in regions rich in gas and ice, where large cores could gather thick atmospheres. Then hot Jupiters were discovered. These are gas giants orbiting extremely close to their stars. Their presence raised a calm question. Did they form there, or did they move there? Many models suggest migration. A giant planet may form farther out in a young planetary disk. Then interactions with the disk, or with other planets, can change its orbit. It can spiral inward, or be thrown into a closer path. Over time, tides can circularize the orbit, leaving a giant world near the star. This process shows that planetary systems are not always born in their final shapes. In youth, a system can be crowded with gas, dust, and growing bodies. Gravity can shift orbits. Planets can push and pull one another. Some worlds may move inward. Others may be scattered outward. Some may be ejected completely. Migration is not chaos without pattern. It is nature seeking balance through motion. A planet's present location may be the last page of a long story. Hot Jupiters therefore become clues to the early histories of systems. Their tight orbits suggest past movement, interaction, and settling. A giant planet near its star is not merely strange, it is a fossil of motion, preserved in orbit. Planet formation begins in disks of gas and dust. Young stars are often surrounded by protoplanetary disks. These disks are wide, rotating structures made of gas, dust, ice, and tiny solid particles. Within them, planets begin as very small grains. At first, the process is quiet and delicate. Dust grains collide and stick. They become clumps. Clumps become pebbles. Pebbles gather into larger bodies. Over time, gravity becomes more important. Growing objects attract more material. Planetesimals form. Some become planetary embryos. Some continue gathering material until they become full planets. The details are complex, and scientists continue to study them. But the broad story is beautifully simple. Stars form from clouds. Around many young stars, leftover material settles into disks. Inside those disks, small pieces meet and build larger worlds. Observatories such as ALMA have seen striking details in protoplanetary disks, including rings and gaps. These patterns may be shaped by forming planets, dust growth, snow lines, or other processes. The disk is not a flat, empty plate. It is a changing environment where gravity, chemistry, and motion work together. In such disks, the ingredients of planets begin to separate by temperature. Close to the star, heat favors rock and metal. Farther out, ices can survive. This helps explain why some planets become rocky, while others gather more gas and ice. A planet is not made all at once. It begins as dust, learning, slowly, how to gather. Snowlines help shape the materials of planets. In a protoplanetary disk, temperature changes with distance from the young star. Close in, it is warm. Farther out, it is cooler. At certain distances, specific substances can freeze into solid ice. These boundaries are called snowlines, or ice lines. The water snow line is especially important. Inside it, water tends to remain vapor. Outside it, water can freeze onto dust grains. Icy grains are stickier and more abundant in solid material, making it easier for large cores to grow. This may help giant planets form beyond the snow line, where there is more solid building material available. Other substances have their own frost lines. Carbon dioxide, methane, and ammonia freeze at different temperatures. Each one adds to the chemistry of growing planets in different regions. The snow line is not a sharp painted circle. It can move as the star and disk evolve. A young star may be brighter at first. The disk may cool over time. Material can drift inward or outward. Still, the concept helps explain why planets forming in different places can have different compositions. Earth formed in the warmer inner solar system, but it still gained water. That water may have arrived through several pathways, including water-bearing materials from farther regions. Planetary formation is a story of both location and movement. In distant disks around young stars, snow lines quietly mark where vapor becomes frost. From such soft boundaries, the ingredients of worlds begin to change. Resonant planets move in linked rhythms. In some systems, planets orbit in patterns where their periods form simple ratios. For example, one planet may orbit twice for every one orbit of another, or 3 times for every 2. These relationships are called orbital resonances. Resonances happen because planets tug on each other through gravity. If their orbital periods line up in certain ways, those tugs repeat regularly. Over time, the planets can become locked into a stable pattern. TRAPPIST-1 is a famous example of a resonant chain. Its 7 planets move in connected rhythms. The timing of their transits shifts slightly because they pull on one another. Those shifts help scientists estimate their masses. The idea feels almost musical. Each planet has its own orbit, but none moves entirely alone. Their periods relate. Their gravity speaks across space. The system keeps time as a family. Resonances can also reveal history. Planets may move through a disk and become trapped in linked orbits. If a resonant chain remains, it may preserve evidence of migration and gentle settling. If it breaks, the system may become more widely spaced or dynamically changed. In the solar system, some moons and planets also show resonant relationships. Jupiter's moons Io, Europa, and Ganymede form a famous resonance. This shows that the same gravitational principles work across many scales. A resonant exoplanet system is not only a group of worlds, it is a quiet clock made from gravity. Planet density helps reveal what a world may be made of. Density is found by combining mass and size. Mass can often be estimated through radial velocity or transit timing variations. Size can be estimated when a planet transits its star. Together, these measurements allow scientists to calculate average density. A dense planet may be rich in rock and metal. A low-density planet may contain a large amount of gas, ice, or an extended atmosphere. Earth has a high enough density to show its rocky and metallic nature. Saturn has such low average density that it is famously less dense than water, though that does not mean it has a surface like an object floating in a bowl. For exoplanets, density is a first window into composition. A planet the size of Earth but much more massive could have a large iron core. A planet larger than Earth but with low density might be wrapped in gas or contain abundant water. A giant planet with an inflated radius may have a very low density compared with its size. But density alone is not a complete answer. Many different interiors can produce similar average densities. A planet might have rock, water, gas, and metal in several combinations. Scientists use models to explore what mixtures are possible. Still, the measurement is powerful. From a shadow and a wobble, astronomy can begin to weigh a distant world and guess what fills its interior. A planet's body remains far away, but its density gives a soft outline of what it may hold. Some planets are darker than charcoal. The brightness of a planet depends partly on its albedo, meaning how much light it reflects. A high albedo world reflects a lot of light. A low albedo world absorbs most of it. Snow and clouds can be bright. Dark rock, deep oceans, or certain atmospheric chemicals can absorb more light. Some hot Jupiters are extremely dark. They orbit close to their stars, yet reflect very little visible light. Their atmospheres may contain gases that absorb starlight strongly. Clouds that would reflect light on cooler planets may not form in the same way at such high temperatures. A dark planet near a bright star is difficult to see. It does not shine by its own visible light, and it reflects little of the star's light. But it may glow in infrared because of its heat. Telescopes can sometimes measure this thermal glow, especially when the planet moves behind its star and the combined light drops slightly. This is called a secondary eclipse. First, the planet passes in front of the star during a transit. Later, it passes behind the star. When it disappears behind the star, the telescope briefly receives only the star's light, not the planet's glow. The tiny difference reveals something about the planet's brightness and temperature. Even darkness becomes measurable with enough care. A world can hide much of the light it receives and still tell its story in warmth. Some exoplanets are brighter than expected. While some worlds are dark, others may reflect a great deal of light. A planet's brightness depends on clouds, haze, surface material, and atmospheric chemistry. Thick clouds can act like mirrors, sending starlight back into space. Ice can also brighten a planet, while dark rock or oceans can absorb more. Venus is the familiar example from our own sky. It shines brightly because its thick cloud layers reflect sunlight. An exoplanet with high reflective clouds could also be bright, though seeing that reflected light is difficult across interstellar distances. Brightness can change with phase. Just as the moon shows phases from Earth, an exoplanet can show different amounts of its day side as it orbits. Sensitive telescopes can measure phase curves, tracking how the total light of a star-planet system changes over an orbit. From a phase curve, scientists can learn how heat is distributed around a planet. If the hottest region is shifted away from the point directly beneath the star, winds may be moving heat around the atmosphere. If the night side is warm, heat transport may be efficient. If the day side is much hotter, circulation may be weaker. The planet remains unseen as a detailed globe, but its changing light becomes a soft map. Brightness, like shadow, is a language. In the faint rise and fall of light, a distant atmosphere turns slowly into knowledge. Exoplanets make Earth feel both small and deeply rare. Thousands of confirmed planets now fill catalogs, and many more candidates wait to be verified. This abundance changes the old feeling of the cosmos. Planets are not unusual decorations around a few stars. They seem to be a common outcome of star formation, and yet Earth remains singular in human knowledge. It is still the only world known to hold life. It has liquid oceans on its surface, a breathable atmosphere for its creatures, active geology, a protective magnetic field, and a long history written in stone and cells. The discovery of many planets does not make Earth ordinary in every way. It makes planets ordinary as a category, while leaving living worlds mysterious and precious. There may be many rocky planets. There may be many worlds in habitable zones. But whether life begins often, rarely, or almost never remains one of the quietest questions in science. Exoplanets widen the mind without taking away the value of home. They show that Earth is part of a vast planetary family. They also show how many things must work together for a world to become gentle enough for forests, rain, sleep, and memory. A distant planet may teach about heat. Another may teach about atmosphere. Another may teach about formation. Earth teaches what is possible when conditions remain steady for billions of years. The galaxy is rich with worlds, and among them one blue planet is the place where eyes look back. 55 Cancri is a super-Earth, so close to its star that rock may melt. This planet is also called Janssen. It orbits a star in the constellation Cancer. about 41 light-years from Earth. The planet is larger than Earth and much more massive, but still smaller than Neptune. Its orbit is extremely tight. 1 year on 55 Cancri A lasts less than 1 Earth day. Because it moves so close to its star, the planet receives intense heat. Many models suggest that part of its surface may be molten, perhaps forming a vast lava ocean on the day side. The idea is strange, but it follows ordinary physics placed in extraordinary conditions. Rock is solid on Earth's surface because temperatures are gentle enough. Raise the temperature high enough, and stone begins to flow. 55 Cancri A may also have an atmosphere, though its exact nature has been difficult to understand. Observations have suggested that heat moves around the planet in complex ways. The hottest region may not always sit exactly beneath the star. That can hint at circulation, surface flow, or atmospheric movement. The planet reminds astronomy that even rocky worlds can be very different from Earth. A rocky composition does not guarantee mountains, deserts, oceans, or quiet continents. Around another star, rock can become a glowing sea. The same minerals that make familiar ground can soften into light beneath a nearer sun. On some worlds, a year is shorter than a single Earth day. Ultra-short period planets orbit their stars in less than 24 hours. They are usually very close to their stars, moving quickly through strong gravity. Their orbits are small, tight, and fast, like beads circling near the center of a spinning wheel. GJ367b is one of these worlds. It orbits a nearby red dwarf star every few hours. It is smaller than Earth, and studies suggest it is unusually dense. That density may mean it has a large iron-rich interior, somewhat like an extreme version of Mercury's heavy core. A planet so close to its star is shaped by heat and radiation. If it once had a lighter atmosphere, much of it may have been stripped away. What remains could be a dense inner body, the durable part of a world that has spent a long time under intense starlight. Ultra-short period planets are valuable because they test ideas about planetary survival. They ask how close a rocky planet can orbit before it changes beyond recognition. They show what remains after heat, tides, and time have done their slow work. The motion itself is graceful from far away. A tiny planet crosses its star again and again. Each transit arrives quickly. Each orbit completes with steady rhythm. A whole year passes while Earth is still turning through a single day. Mercury helps explain some close-in exoplanets. Mercury is the innermost planet in the solar system. It is small, rocky, and unusually rich in metal compared with Earth. It orbits close to the Sun and has almost no atmosphere. Its surface records ancient impacts, long cooling, and the patience of solar light. Some exoplanets seem to echo parts of Mercury's story, though often in more extreme ways. Small, dense worlds close to their stars may have large iron cores. They may have lost lighter outer material during formation, impacts, or long exposure to stellar radiation. They may be bare, compact remnants of more complicated histories. GJ367b is sometimes discussed in this broader context because of its density and short orbit. It is not Mercury's twin. It orbits a different kind of star, at a different distance under different conditions. But Mercury gives a familiar starting point for imagining how a rocky world can become metal-rich and airless. The comparison is gentle and useful. The solar system is not a perfect template, but it is a nearby library. Earth teaches one lesson, Venus another, Mars another. Mercury teaches how close light, small size, and rocky metallic interiors can combine. When scientists study distant worlds, they often begin with nearby ones. The planets at home become quiet keys to planets far away. K2 Beta18b is a sub-Neptune in the habitable zone of a cool star. It orbits a red dwarf star, about 120 light-years away. The planet is much more massive than Earth and larger in radius, placing it in the sub-Neptune category. It is not an Earth twin. It is a different kind of world, larger, heavier, and likely wrapped in a substantial atmosphere. K2 Beta18b is interesting because it orbits in the habitable zone of its star. It receives an amount of light that raises questions about whether liquid water could exist somewhere in its environment, depending on its atmosphere and interior. But this idea must remain careful. A habitable zone orbit is not proof of a habitable surface. The James Webb Space Telescope has observed the planet's atmosphere during transits. Webb data revealed carbon-bearing molecules, including methane and carbon dioxide. These detections are important because they show how modern telescopes can study the chemistry of smaller, temperate exoplanets. Some interpretations suggest that K2 Beta b could belong to a proposed class called Hycean worlds. These would be planets with hydrogen-rich atmospheres and possible global oceans beneath. The idea is still being tested. It is not a confirmed picture of the planet. K2 Beta 18b is valuable because it sits between categories. It is not a simple rocky Earth. It is not a giant like Jupiter. It is a middle world, wrapped in questions. In its atmosphere, distant starlight carries careful clues. Hycean worlds are imagined as ocean planets beneath hydrogen-rich skies. The word Hycean combines hydrogen and ocean. It describes a proposed class of exoplanets that may have deep global oceans under thick hydrogen-rich atmospheres. Such worlds would be larger than Earth but smaller than Neptune, perhaps similar to some sub-Neptunes already discovered. The idea matters because it expands how scientists think about habitability. For a long time, the search focused mostly on rocky Earth-like planets. That remains important. But life's requirements may not point to only one planetary design. If a world has liquid water, useful chemistry, and stable conditions, it may be worth studying even if it is not Earth-sized. Still, Hycean worlds are theoretical. Each candidate must be examined with caution. A planet may be too hot beneath its atmosphere. Its pressure may be too high. Its ocean, if present, may not be accessible to life as known on Earth. Its atmosphere may create conditions that are not gentle at the water layer. K2 Beta 18b is often discussed in relation to this idea, but scientists do not yet know whether it truly has an ocean. The word possible carries most of the weight. Hycean worlds are therefore not conclusions. They are questions with soft edges. They invite telescopes to look more closely at planets that do not fit the familiar Earth template. The search for life may need more than one image of home. Some possible oceans may rest beneath skies unlike any on Earth. Possible biosignatures must be treated with patience. In exoplanet science, a biosignature is a possible sign of life. It may be a gas, a surface feature, or a chemical imbalance that living processes could produce. On Earth, oxygen, methane, and certain sulfur compounds are connected in different ways to biology, geology, atmosphere, and sunlight. But a possible biosignature is not proof. A molecule associated with life on Earth may have non-living sources elsewhere. Chemistry can be surprising. Planets can produce gases through volcanism, photochemistry, impacts, water-rock reactions, or unknown processes. A single detection, especially from a very distant planet, must be tested carefully. K2 Beta 18b has received attention because Webb observations included discussion of possible dimethyl sulfide, a molecule that on Earth is produced by living organisms. Later work and further observations are needed to confirm the signal and understand possible sources. The calm scientific position is simple. It is interesting, but not settled. This patience protects wonder. It keeps the story honest. A premature answer can make the universe feel smaller. A careful question leaves it wide. The search for life beyond Earth may someday bring one of the deepest discoveries in history. But such a discovery will need many lines of evidence, repeated measurements, and careful comparison with non-living explanations. In the soft light of another star, chemistry may whisper. Science listens slowly, without rushing the meaning. L9859 is a nearby system with several small planets. The star is an M-dwarf, smaller and cooler than the Sun. It lies about 35 light-years away, making it relatively close in astronomical terms. Around it, astronomers have found multiple planets, including small rocky worlds and super-Earth candidates. L9859b, C and D were first discovered with tests through the transit method. Because the planets cross in front of their star, their sizes can be measured from the dips in starlight. Follow-up observations help estimate masses and densities. L9859d is especially interesting because it is larger than Earth and may contain a significant amount of lighter material. Some studies have explored whether the system includes planets with different compositions, from rocky inner worlds to worlds that may hold more water or atmosphere. A system like L9859 is valuable not because it contains a confirmed second Earth, but because it offers comparison. Several planets orbit the same star. They likely formed from the same original disk, yet each one may have followed a different path. Their sizes, masses, and distances can be studied together. This is like finding several stones from the same river and noticing how each has been shaped differently. One is smooth, one is dense, one is pale, one is darker. Their shared origin makes their differences meaningful. Around a small nearby star, a family of worlds keeps several quiet records of formation. Planet families help reveal the history of a system. A single exoplanet can teach a great deal, but several planets around the same star can teach even more. Their spacing, sizes, masses, and orbital rhythms become clues to how the system formed and changed. In some systems, planets are packed close together. They may have short years and regular transits. In others, giant planets move farther out, taking many years to complete their orbits. Some systems have resonances, where the planet's orbital periods form linked patterns. Others look more scattered. The solar system itself is a family. The inner planets are rocky. The outer planets are giant and colder. Asteroids, comets, dwarf planets, and moons fill in the story. Around other stars, planet families can be arranged differently. Large planets can orbit close in. Small planets can form compact chains. Neptune-sized planets can appear where the solar system has no equivalent. When astronomers find several planets around one star, they can compare them under shared starlight. The same star shines on all of them, but each distance creates a different environment. The inner planet may be hot and bare. The outer one may be cooler. A middle world may be transitional. A planetary system is not only a list of planets. It is an architecture built by dust, gravity, time, and light. Clouds can hide the chemistry of an exoplanet. When scientists study a planet's atmosphere through transmission spectroscopy, they hope to see clear chemical fingerprints. Water vapor, methane, carbon dioxide, sodium, and other molecules can each absorb light in recognizable ways. But clouds and haze can soften or flatten those features. This happens because clouds high in the atmosphere can block starlight from passing through deeper layers. Haze particles can scatter light. Instead of a spectrum full of strong peaks and valleys, the result may look muted. The atmosphere is present, but it keeps some of its details hidden. GJ12 Photon 4b is a famous example of a planet whose atmosphere has appeared cloudy or hazy in observations. For years, its spectrum did not reveal simple, strong features. That made the planet mysterious, but also scientifically important. A hidden atmosphere is still an atmosphere. Clouds are familiar on Earth, but they are not always made of water. On hot exoplanets, clouds might contain silicates, metals, salts, or other compounds. On cooler worlds, they might involve water, methane, or ammonia. The ingredients depend on temperature, pressure, and chemistry. A cloud is a kind of veil. It can brighten a planet, cool a planet, warm a planet, or conceal a planet's lower air. In the spectra of distant worlds, silence can also be information. Phase curves show how heat moves around a planet. A phase curve measures how the brightness of a star-planet system changes as the planet orbits. When more of the planet's day side faces the telescope, the system may appear slightly brighter. When more of the night side faces the telescope, it may appear slightly dimmer. The changes are tiny, but they can reveal important details. For close-in planets, especially hot Jupiters, infrared phase curves can show how heat is distributed. If the hottest part of the planet is shifted east or west of the point directly facing the star, winds may be moving heat around the globe. On Earth, weather carries heat from place to place. Oceans and air help smooth temperature differences. On a hot Jupiter, winds can be far faster, and the planet may be tidally locked. The day side receives constant starlight. The night side receives none. Between them, atmosphere becomes a bridge. Phase curves help scientists understand that bridge. A warm night side suggests efficient heat transport. A cold night side suggests that heat stays mostly on the day side. A shifted hotspot reveals circulation. The planet remains a point of light. No continents or storms are seen in detail, yet the changing brightness becomes a soft thermal map. As the planet turns through its orbit, warmth rises and fades in the data. A distant world reveals its weather by glowing slightly out of rhythm. Secondary eclipses help measure a planet's own light. A transit happens when a planet passes in front of its star. A secondary eclipse happens when the planet passes behind the star. During that moment, the telescope receives light from the star alone, without the planet's reflected light or thermal glow. The difference is very small, But with sensitive instruments, it can be measured. By comparing the total light before, during, and after the eclipse, scientists can estimate how much light came from the planet. In visible wavelengths, this can tell something about reflected starlight and albedo. In infrared wavelengths, it can tell something about the planet's heat. This is especially useful for close-in giant planets, which are warm enough to glow strongly in infrared. Secondary eclipses can also help study atmospheric composition. If the planet's dayside spectrum is measured before it disappears, molecules in the atmosphere may leave patterns in the emitted light. This is different from transmission spectroscopy, which studies starlight passing through the atmosphere at the planet's edge. Both methods are ways of reading light. One studies the rim of the planet during transit. The other studies the glowing face of the planet before it slips behind the star. The planet itself vanishes for a short time. In that absence, its faint contribution becomes clearer. Some exoplanets may have diamond-like minerals, but not simple diamond worlds. There has been popular talk about carbon-rich planets and diamond planets. The real science is more careful. If a planet forms in an environment with more carbon relative to oxygen, its minerals may differ from Earth's. Instead of silicate rocks dominating, carbon compounds and carbides could be more common. Under high pressure, some carbon might take diamond-like forms. 55 Cancri was once discussed in this context, because its host star was thought by some studies to be carbon-rich. Later work made the picture more uncertain. The planet is now more often described as a super-hot super-Earth, possibly with molten rock or a thick atmosphere, rather than a confirmed diamond world. This is a useful lesson in how science changes. Early measurements suggest one possibility. Better measurements refine it. A headline may linger, but the scientific picture becomes more detailed and more cautious. There may indeed be planets with unusual carbon chemistry. The universe has made many stars with different compositions. Planetary disks inherit those ingredients. A world born in a carbon-rich disk could build rocks unlike Earth's rocks, but the calm truth is better than exaggeration. Exoplanets do not need to be made of treasure to be wonderful. Their real chemistry is already enough. A distant world may not be a jewel. It may be something quieter and stranger. A planet shaped by carbon, heat, and time. Starlight can separate planets into different futures. A star is not only a lamp, it is an environment. It gives visible light, infrared warmth, ultraviolet radiation, flares, particles, and long-term change. Planets respond to all of it. A close planet may lose atmosphere. A farther planet may keep ice. A planet around a calm star may preserve conditions for a long time. A planet around an active young red dwarf may face strong radiation early in its history. The same planet placed around a different star could have a different fate. Starlight affects climate, chemistry, clouds, and atmospheric escape. It can split molecules high in the atmosphere. It can create hazes. It can warm surfaces or evaporate oceans. It can also provide the energy that drives weather, and on Earth, supports photosynthesis. This is why the star must always be part of the planet's story. An exoplanet is never just a world alone. It is a world in relationship. Its orbit, atmosphere, rotation, and history all respond to the star it follows. The habitable zone is only one part of that relationship. The star's age, activity, spectrum, and brightness matter too. A planet receives more than light from its sun. It receives a long, slow shaping, written across every layer of air and stone. The search for exoplanets is also the search for patterns. Thousands of discoveries could feel like a scattered collection of names and numbers. But slowly, patterns appear. Hot Jupiters are rare but easy to detect. Super-Earths and mini-Neptunes are common. Small planets often gather around small stars. Some systems are compact and resonant. Some planets lose atmospheres. Some giants inflate under heat. These patterns help scientists move from discovery to understanding. A single planet is a fact. A population of planets becomes a story. When many worlds are measured together, astronomers can ask how planets form, how they migrate, how they keep or lose atmospheres, and how often rocky worlds appear in temperate orbits. The field is still young. The first confirmed planet around a sun-like star was found only a few decades ago. Since then, the map has filled quickly, yet it is still incomplete. Many planets remain too small, too distant, too cold, or too widely orbiting to be easily found. Every telescope has its own bias. Transits favor planets whose orbits line up with Earth. Radial velocity favors massive planets close to stars. Direct imaging favors young giants far from stars. Microlensing finds moments that may not repeat. Together, the methods form a wider view. Each technique catches a different kind of whisper from the same planet-filled galaxy. Kepler 10b was one of the first clearly rocky worlds found by Kepler. It orbits a star somewhat like the Sun, though far away in the constellation Draco. The planet is larger than Earth, but not large enough to be a gas giant. Its measured size and mass show that it is dense, and that density points toward a rocky composition. Kepler 10b moves very close to its star. Its year lasts less than one Earth day. In that time, while Earth has not yet completed a single rotation from one midnight to the next, Kepler 10b has already circled its star and begun again. A close orbit means strong heat. The planet is not a gentle Earth-like place. It is likely too hot for familiar surface conditions. Its day side may be heated enough for rock to soften or melt. Yet its importance is not in comfort. Its importance is in conformation. It helps show that small, dense planets could be found around other stars with precise starlight measurements. Kepler detected the planet through the transit method, a tiny dip in brightness repeated with steady timing. Follow-up measurements helped estimate its mass. Together, the measurements turned a dimming pattern into a rocky world. The discovery carried a quiet kind of wonder. The telescope did not see mountains or plains. It saw rhythm. It saw a star's brightness lower by a tiny amount. From that softness, a new category of certainty appeared. A distant star dimmed slightly, and in that small shadow, a rocky planet came into focus. Technosignatures 7b helped reveal the age of close-in rocky planets. It was discovered by the French-led Corot space mission, whose name comes from convection, rotation, and planetary transits. Like Kepler, Corot searched for planets by watching stars dim when planets crossed in front of them. Corot 7b is a super-Earth orbiting extremely close to its star. Its year lasts less than one Earth day. It is larger and more massive than Earth, and its tight orbit places it under strong heat. Many descriptions of the planet have imagined a surface where rock may be molten on the star-facing side. This planet belongs to the early history of small exoplanet discoveries. Before many rocky worlds were known, Corot 7b showed that the search was reaching beyond giant planets. Astronomers were beginning to detect smaller, denser worlds, even when they moved in tight and difficult environments. The planet also reminds science that rocky does not mean Earth-like. A world can be made mostly of rock and metal, yet still be very unlike home. Its skies, if any, may be shaped by vaporized minerals. Its surface may be dark, glowing, or changing under heat. Its orbit may be so short that the concept of seasons feels almost irrelevant. Still, the planet's existence is gentle evidence of abundance. Rocky material gathers around other stars. It forms planets. Some become temperate, some become scorched, some remain unknown. The same ingredients that build quiet mountains here can form molten landscapes elsewhere. Close-in rocky planets may be stripped cores. Some small planets near their stars may not have always looked the way they do now. They may be the remaining dense centers of worlds that once had more gas, more ice, or thicker outer layers. Over time, strong starlight can remove lighter material. Impacts can also reshape a planet. Migration can move a world into a harsher orbit. A stripped core is the surviving interior of a planet. It is like seeing the heartwood of a tree after the bark and outer rings have been worn away. Around a star, this process is not carved by wind or rain, but by heat, radiation, impacts, and gravity. Mercury in the solar system offers a nearby clue. It is unusually rich in metal compared with the other rocky planets. Scientists still study why. It may have formed from metal-rich material, or it may have lost part of its rocky mantle through early impacts or solar effects. Around other stars, similar questions become larger and more varied. A planet close to its star may lose an atmosphere first. If it began as a mini Neptune, with a rocky core wrapped in hydrogen and helium, the outer gas might escape. What remains could be a super-Earth, or a dense rocky body. These ideas help connect different planet sizes. They suggest that some categories may be related by history, not only by birth. A small world can be a survivor. Its present shape may be the quiet remainder of an earlier self. A planet's orbit can be stretched into a long oval. Many planets have orbits that are close to circular. Earth's orbit is slightly elliptical, but nearly round. Some exoplanets, however, follow strongly stretched paths. They move far from their stars, then sweep inward much closer, then move outward again. This stretched shape is called eccentricity. A circular orbit has low eccentricity. A long oval has high eccentricity. Eccentric orbits can form through gravitational interactions with other planets or stars. A planet may be pulled, scattered, or gradually reshaped into a path that is far from round. A highly eccentric orbit changes the planet's environment during each year. Far from the star, it receives less heat. Near the star, it receives much more. The change can happen quickly near closest approach, because the planet moves fastest there. The rhythm is different from Earth's seasons. Earth's seasons come mostly from axial tilt, not from large distance changes. On an eccentric exoplanet, the star itself may appear to grow dramatically brighter during one part of the orbit, then soften again as the planet recedes. This kind of orbit tells a story of dynamical history. It may hint that the planet once interacted with another massive body. It may show that the system has not settled into the calm circular pattern familiar from many diagrams. A planet's path can be a memory. In the shape of its orbit, gravity preserves an old encounter. HD 8606b follows one of the most stretched known orbits. It is a massive gas giant orbiting a star in a binary system. Its orbit is highly eccentric, meaning it is drawn into a long oval rather than a near circle. For much of its orbit, the planet remains relatively far from its star. Then it swings inward, passing much closer for a short time. The journey takes about 111 Earth days. During that year, the planet experiences a large change in starlight. Near closest approach, the amount of energy it receives rises quickly. The atmosphere responds to the sudden heating, then cools as the planet moves away again. This makes HD 86006b an extraordinary laboratory for atmospheric physics. It is not merely hot all the time like many close-in hot Jupiters. Instead, it receives a periodic pulse of heat. Scientists can study how the atmosphere reacts when the energy changes rapidly. The orbit itself may have been shaped by gravitational interactions. The planet's star has a distant stellar companion, and such arrangements can influence planetary orbits over long times. Gravity works patiently, sometimes shifting paths across millions of years. From far away, HD 8606b is known through measurements, not through a close image, yet the pattern is vivid. A giant world moves along a long curve, quiet for much of its year, then brightened by a near passage. Its orbit is like a slow breath, far from the star, then near, then far again. Eccentric planets show that systems can remain restless for a long time. A solar system can look stable, but stability does not always mean perfect circles. Planets may keep returning along stretched paths for billions of years. Their orbits can be predictable and still dramatic in shape. Eccentricity matters because it changes climate and tides. A rocky planet on a highly eccentric orbit might receive very different amounts of heat during different parts of its year. If it has oceans or an atmosphere, those systems would need to absorb and redistribute changing energy. If it lacks air, the surface temperature could swing widely. For giant planets, eccentricity can heat interiors through tidal forces. When a planet moves closer to and farther from its star, the star's gravity can flex the planet slightly. That flexing can generate heat inside, especially if the orbit is strong and the planet is large. Eccentricity also reveals past interactions. A planet does not usually become highly eccentric without help. Another planet may have scattered it. A companion star may have tilted or stretched the orbit. The disk itself may have played a role. In this way, an orbit becomes a fossil of movement. It remembers pulls that may no longer be visible. A missing planet, a distant star, or an ancient migration can leave behind a curve. A round orbit speaks of settled balance. A stretched orbit whispers that gravity has been busy. Directly imaged planets are often young and warm. Seeing an exoplanet directly is one of the most difficult tasks in astronomy. A planet is faint beside its star. The star's glare spreads across the telescope image, hiding anything nearby. To find the planet, astronomers often need special instruments that block or reduce starlight. Young giant planets are among the easiest to image. They still hold heat from formation. In infrared light, they glow more strongly than older, colder planets. If they orbit far from their stars, they are also easier to separate from the star's glare. This means direct imaging does not find every kind of planet equally. It favors large, young, warm worlds at wide separations. Many small rocky planets remain beyond its reach. A planet like Earth, close to a sun-like star and shining mostly by reflected light, is still a very difficult target. But when direct imaging succeeds, it gives a special kind of evidence. The planet is not only inferred from a wobble or a shadow, it appears as its own faint point of light. Over years, that point may move in orbit, slowly tracing its path around the star. The image may look simple. A star is blocked, a tiny dot remains. Yet the dot is a planet, glowing with the warmth of youth. In that faint point, a distant world is seen almost directly by human eyes. Beta Pictoris is a young giant planet seen beside a dusty star. Beta Pictoris is a young star surrounded by a disk of dust and debris. For decades, this disk made the system important to astronomers studying planet formation. The disk appeared warped and structured, suggesting that unseen planets might be shaping it. Then Beta Pictoris b was directly imaged. It is a massive gas giant orbiting far from its star, at a distance similar to the outer regions of our solar system. The planet is young and warm, glowing in infrared light. Its orbit has been tracked over time, showing real motion around the star. This system is beautiful because it connects several ideas at once. There is a young star, there is a disk of material, there is a giant planet embedded in the wider architecture. The planet and disk are part of the same story: how young systems settle after their formation. Beta Pictoris b is not a small rocky world. It is not an Earth candidate. Its value lies elsewhere. It shows how planets can be photographed when they are young, warm, massive, and far enough from the glare of the star. The dusty disk is like a soft ring of memory around the star. It contains leftovers from formation, collisions, and small bodies. The planet moves within this environment, shaping and being shaped by it. A young world glows beside a young star. Around them, dust keeps the early history of a system. HR 8799 has several giant planets seen in direct images. The HR 8799 system is one of the most famous examples of direct imaging. Around the star, astronomers have photographed multiple giant planets. They orbit far from the star, much farther than Earth is from the Sun. Over time, observations show them moving in their orbits. The system feels almost like a slow celestial mobile. Several massive planets circle the same star, each one taking many decades or centuries to complete an orbit. The movement is too slow for a single night, but patient observations across years reveal the pattern. Direct imaging of HR 8799 helps scientists study young giant planets because their light can be separated from the star's glare. Their atmospheres can be examined. Spectra can reveal molecules, clouds, temperatures, and broad atmospheric properties. These planets challenge formation models. Giant planets so far from a star are not always easy to explain. Did they form there directly from the disk? Did they form closer in and move outward? Did gravitational interactions arrange them into their present paths? The system remains a calm puzzle. The planets themselves appear as tiny points, but they carry deep information. Their colors and spectra speak of clouds and chemistry. Their orbits speak of mass and stability. Their arrangement speaks of formation. A directly imaged system does not show landscapes. It shows a family of young giants moving slowly through their own wide dark. PDS-70 contains planets still connected to their birth disk. PDS-70 is a young star surrounded by a disk of gas and dust. Within that disk, astronomers have found planets, including PDS-70b and PDS-70c. This makes the system especially important because it offers a glimpse of planet formation still in progress. The planets have carved gaps and cavities in the disk as they gather material and interact with their surroundings. They are not finished objects sitting in an empty system. They are young worlds in a place still rich with the material of formation. PDS-70c is especially interesting because observations have revealed a circumplanetary disk around it. A circumplanetary disk is a smaller disk around a planet rather than around a star. Such disks are thought to be places where moons can form. This creates a layered image. A star has a disk. Inside the star's disk, a planet grows. Around the planet, a smaller disk forms. Inside that smaller disk, moons may begin. The architecture of formation repeats at a smaller scale. In our solar system, the large moons of Jupiter and Saturn may have formed in disks around those giant planets. PDS-70 gives scientists a distant, young example where similar processes may be observed more directly. It is one thing to infer that planets formed long ago. It is another to see young planets still surrounded by the material of their making. Circumplanetary disks may be nurseries for moons. A planet forming inside a protoplanetary disk can gather material not only into its own body, but also into a smaller disk around itself. Gas and dust flow toward the planet. Some material falls in, some settles into orbit. From that orbiting material, moons may form. This is called a circumplanetary disk. It is the planetary version of a protoplanetary disk. The scale is smaller, but the idea is similar. Dust and gas orbit a central body. Material collides, sticks, gathers, and grows. The giant planets in the solar system carry moon systems that may preserve evidence of such disks. Jupiter's large Galilean moons, for example, orbit in a regular pattern and may have formed in a disk around young Jupiter. Saturn's moons also hint at a rich history of material orbiting a forming planet. In exoplanet systems, observing circumplanetary disks is difficult. They are small, faint, and embedded in bright surroundings. But systems like PDS-70 offer a chance. When astronomers see a disk around a young planet, they are looking at a possible moon-forming environment. This adds another layer to exoplanet wonder. A planet is not always the end of formation. It may become a center of formation itself. Around it, smaller worlds may begin to gather. A young planet can have its own quiet ring of beginnings. Inside that ring, future moons may be learning how to form. Exomoons may exist, but they are difficult to confirm. An exomoon is a moon orbiting a planet beyond our solar system. Since moons are common around the giant planets here, it seems reasonable that many exoplanets may also have moons. But finding them is much harder than finding planets. A moon is usually smaller than its planet. Its transit signal is faint. It may cross the star before or after the planet, creating a tiny extra dip in brightness. It can also tug on the planet, shifting the timing or duration of the planet's transit. These effects are subtle and can be confused with noise or other activity. Several possible exomoon candidates have been discussed, but confirmation remains very challenging. The data must be strong, repeated, and carefully separated from other explanations. For now, exomoons remain one of the quiet frontiers of exoplanet science. The idea is still beautiful. Around a distant giant planet, a moon may circle in darkness. It may be icy, rocky, volcanic, or ocean-bearing. It may never pass in front of the star from Earth's viewpoint, leaving no easy signal. It may exist without being known. Moons matter because they can be worlds in their own right. In the solar system, moons hold oceans, volcanoes, atmospheres, and complex surfaces. Beyond the sun, they may add even more variety. A planet can be a world, a moon can be another world, softly bound beside it. Brown dwarfs sit near the boundary between planets and stars. A brown dwarf is more massive than a planet, but not massive enough to sustain ordinary hydrogen fusion like a true star. Some can briefly fuse deuterium, depending on mass, but they never shine steadily like stars such as the sun. This makes them fascinating boundary objects. They form in ways that may resemble stars, from collapsing clouds of gas. Yet they can have atmospheres with clouds, storms, and temperatures that overlap with giant planets. Some are warm and glowing when young. Others cool over time and become faint. The boundary between a massive planet and a low-mass brown dwarf is not always simple. Mass is one guide, but formation history also matters. Did the object form in a disk around a star, like a planet, or did it form alone from a collapsing cloud like a star? Observations cannot always answer easily. Some objects called planetary mass companions orbit stars at wide distances. Some free-floating objects have masses similar to giant planets. The universe does not always arrange itself neatly into human categories. Brown dwarfs remind science that labels are tools, not walls. They help organize knowledge, but nature often places objects between them. In the quiet borderland between planet and star, brown dwarfs cool slowly, carrying traits of both. Metallicity can influence whether giant planets form. In astronomy, metals mean elements heavier than hydrogen and helium. a star with higher metallicity formed from material richer in heavy elements. Since planets are built from dust, ice, rock, and metal, the chemical composition of a young star's disk matters. Studies have shown that giant planets are more common around stars with higher metallicity. This makes sense in the core accretion model of planet formation. To build a gas giant, a solid core may need to form quickly enough to gather gas before the disk disperses. More heavy elements can mean more solid material, helping cores grow. This does not mean lower metallicity stars cannot have planets. Small rocky planets appear around a wide range of stars. But for giant planets, the connection with metallicity is an important clue. A star's composition is like a record of the cloud that made it. The disk around the star inherits that chemistry. From the disk, planets form. In this way, the ingredients of a planet are tied to the history of the galaxy itself. Earlier generations of stars created heavy elements and released them into space. Later stars formed from enriched clouds. Around those stars, planet-building materials became more available. A planet begins long before its own star is born. Its ingredients are prepared in older stars and scattered softly into the dark. Exoplanet names are quiet coordinates in a vast catalogue. Many exoplanet names look unusual at first. Kepler 10 b51 Pegasi b, HD 8066 b, Trappist 1, ELHS 140 b. These names are not designed as poetry. They are designed for identification. Often the first part names the star or survey. Kepler planets were found by the Kepler mission. TESS objects of interest use TOI numbers during candidate stages. HD numbers come from the Henry Draper catalogue. GJ and Gliese names refer to nearby star catalogues. The lowercase letter marks the planet, usually beginning with B for the first planet discovered around that star. The star itself is often considered the primary object. The first planet found is B, not A. Additional planets receive C, D, E, and onward. The order usually follows discovery, not always distance from the star. These names may feel technical, but they are also gentle reminders of scale. There are too many planets for mythic names alone. Catalogue names let astronomers keep track of a sky filled with worlds. Some planets later receive proper names through naming campaigns, but most remain known by their catalogue labels. The labels become familiar through use, like quiet addresses in the galaxy. A name such as Kepler 10b may seem plain, but behind it, a real world circles a real star. The future of exoplanet science is moving towards smaller and cooler worlds. Early discoveries favored large planets close to their stars. These were easier to find. A giant planet makes a stronger wobble. A close planet transits more often. A large world blocks more starlight. The first maps were therefore shaped by what instruments could most easily see. As technology improves, the search moves toward harder targets, smaller planets, wider orbits, cooler atmospheres, rocky worlds around nearby stars, planets that might have temperate surfaces, planets whose atmospheres may hold clues to chemistry, climate, or perhaps biology. This does not mean giant hot planets become unimportant. They remain valuable laboratories. Their strong signals help scientists test instruments and models. Their atmospheres teach lessons that can later be applied to smaller worlds. But the long direction is clear. Astronomy wants to understand planets more like Earth in size and temperature, while also respecting that habitability may take more than one form. Future observatories may study reflected light from rocky planets. They may search for oxygen, ozone, methane, carbon dioxide, water vapor, and other gases in context. They may attempt to separate a planet's tiny glow from the brilliance of its star. The work will require patience, large telescopes, and careful interpretation. Somewhere in the data of future light, a small, cool world may become clearer. Every exoplanet discovery changes the silence between the stars. A star is no longer just a point. It may be the center of a system. Around it, small shadows may cross. Giant planets may tug. Dust belts may glow. Young worlds may gather material. Small rocky planets may keep close orbits. Distant giants may move slowly through wide paths. The night sky has not changed in appearance. The same stars shine overhead, but knowledge changes the feeling of seeing them. The darkness between them becomes less empty. It becomes layered with possible orbits. Exoplanets are not reached by footsteps. They are reached by measurement. They are found through patience, repeated observation, and the careful reading of light. This makes them feel distant, but also strangely intimate. A planet many light years away can touch a telescope not with matter, but with a small change in brightness. That change crosses space. It enters a mirror. It becomes data. It becomes a curve on a screen. Then slowly, it becomes a world in the human mind. The galaxy remains vast. Most worlds are still unknown. But the first quiet map has begun. Beyond the sun, planets are turning, and each one adds a soft point of meaning to the dark. WD 1856b is a giant planet orbiting a white dwarf. A white dwarf is the dense remaining core of a star like the Sun after it has passed through later stages of stellar life. It is small, faint, and compact. It no longer shines by ordinary hydrogen fusion in the way the Sun does. Instead, it slowly cools over enormous stretches of time. WD 1856b is unusual because it is a gas giant, orbiting very close to such a star remnant. Its year lasts about 1.5 Earth days. The planet is much larger than the white dwarf it circles, creating a striking transit when it passes in front of the tiny star. The system raises a quiet question. How did a giant planet come to orbit so close to a white dwarf? During the star's earlier giant phase, nearby planets would likely have faced great changes. WD 1856b may have formed farther away and moved inward later, after the star became a white dwarf. This means the planet is not only a world, it is a record of survival and movement. It suggests that planetary systems can rearrange themselves even after a star changes form. Gravity continues its patient work. Distant companions can tug. Orbits can shift. A planet can arrive close to a stellar remnant long after the original system looked different. Around a small white star, a giant planet moves in a quick and quiet circle. Even after a star changes, planets may continue their long paths. Planets can survive the later lives of their stars. The Sun is stable now, but stars change with age. A star like the Sun eventually expands into a red giant, sheds outer layers, and leaves behind a white dwarf. During these stages, the architecture of a planetary system can shift. Inner planets may be lost or altered. Outer planets, asteroids, and comets may move into new paths. This story matters for exoplanets because many stars in the galaxy are older than the Sun. Some have already become white dwarfs. Around these remnants, astronomers can search for planets, dust, and traces of rocky material. White dwarfs sometimes show heavy elements in their atmospheres. Since heavy elements should sink quickly in a white dwarf's strong gravity, their presence can suggest that rocky material recently fell onto the star. This material may come from asteroids, minor planets, or fragments of once larger bodies. In this way, even the atmosphere of a white dwarf can hold clues about lost planetary systems. The star becomes a quiet archive. Calcium, magnesium, iron, and other elements can hint at the composition of rocky bodies that once orbited nearby. The study of old planetary systems expands the meaning of exoplanet science. It is not only about planets around young or middle-aged stars. It is also about what remains after long stellar change. A planetary system can keep speaking after its star has grown faint. Its story may continue in dust, fragments, and surviving worlds. White dwarfs may help reveal small planetary atmospheres. A white dwarf is about the size of Earth, though much more massive. Because it is so small, a planet passing in front of it can block a large fraction of its light. This makes transits deep and easier to detect in some ways, even for objects that would make very tiny dips around larger stars. If a rocky planet orbited a white dwarf and had an atmosphere, starlight passing through that atmosphere during transit could carry strong signals. The small size of the star would make the relative atmospheric signature larger than it would be around a Sun-like star. This idea makes white dwarf systems interesting for future studies. They are not simple Earth analogues. Their histories are very different. Any close planet must be understood in the context of the star's earlier giant phase and later orbital changes. Still, they may offer a special geometry for atmospheric science. The light source is small. The planet's silhouette is large by comparison. The thin ring of atmosphere, if present, may be easier to notice. The system becomes a natural arrangement for reading filtered light. WD 1856b is a gas giant, not a small rocky planet, but its discovery shows that planets can orbit white dwarfs closely. It opens the door to searching for other systems with different kinds of worlds. Around a star no larger than Earth, a planet's shadow can become wonderfully clear. Biosignatures are not single answers. A biosignature is a possible sign of life. It may be a gas in an atmosphere, a surface pattern, a chemical imbalance, or another feature that living processes might produce. On Earth, life has changed the air, the oceans, and the surface over billions of years. It has filled the atmosphere with oxygen and keeps methane cycling in small but important ways. But a biosignature does not stand alone. Oxygen can be produced in non-living ways under some conditions. Methane can come from geology. Carbon dioxide can be shaped by volcanism, weathering, oceans, and air. A planet can show an interesting molecule without that molecule proving biology. The context matters. What kind of star does the planet orbit? How much ultraviolet light reaches the atmosphere? Does the planet have water? What is its size and mass? Are there clouds? What other gases are present? Does the chemistry seem stable, or is it out of balance? On Earth, oxygen and methane together are interesting because they tend to react with each other. Their continued coexistence suggests active replenishment. But even that idea must be studied carefully when applied to worlds around other stars. The search for life is therefore not a search for one magic word in a spectrum. It is a search for patterns that make sense together. A planet's atmosphere is a sentence, not a single letter. Its meaning comes from the whole quiet arrangement. Oxygen is powerful, but it can be misleading without context. On Earth today, oxygen is strongly connected to photosynthesis. Plants, algae, and cyanobacteria release oxygen as they use sunlight to process carbon dioxide and water. Over long time, this transformed Earth's atmosphere. Because of that, oxygen is one of the most discussed biosignature gases. If oxygen were found in the atmosphere of a rocky exoplanet, especially with other supportive evidence, it would be deeply interesting. But oxygen can also build up without life in some models. For example, strong ultraviolet light can split water vapor high in an atmosphere. Hydrogen can escape more easily to space, leaving oxygen behind. A planet that lost an ocean might retain oxygen even without biology. Other chemical pathways may also create oxygen or ozone in ways that could mimic a biological signal. This does not make oxygen unimportant. It makes it a careful clue. It must be studied with the star, the planet's history, the presence of water, carbon dioxide, methane, and other gases. A single gas cannot carry the whole burden of meaning. The best future biosignature searches will likely use many lines of evidence. They will ask whether an atmosphere is in chemical disequilibrium. They will test non-living explanations. They will compare observations with models of climate, photochemistry, and geology. Oxygen may one day become part of a profound discovery, but science will read it slowly, in the company of other signs. Methane is also a clue that needs surrounding evidence. Methane is a simple molecule made of carbon and hydrogen. On Earth, it is produced by living organisms, geological processes, wetlands, agriculture, fires, and other sources. It also breaks down in the atmosphere over time, especially through reactions driven by sunlight and other chemicals. Because methane does not last forever in many atmospheres, its presence can suggest ongoing replenishment. If methane appears together with oxygen or ozone, the combination can be especially interesting, because these gases can react with one another. A stable atmosphere with both may require continuous sources, but methane is not automatically biological. It can form through water-rock reactions, volcanic activity, or other non-living chemistry. Some planets may produce methane in deep interiors or through interactions between water and certain minerals. Giant planets can also contain methane without life, as seen in the outer solar system. For exoplanets, methane must be interpreted in context. A warm rocky planet with methane, oxygen, water vapor, and a stable climate would invite one kind of question. A hydrogen-rich sub-Neptune with methane would invite another. A cold giant planet would invite another. The molecule is the same. The meaning changes with the world. In a spectrum, methane can be a soft mark of chemistry. It may point to geology. It may point to atmospheric reactions. In the right context, it may someday join a larger life-related pattern. A single molecule whispers. The whole planet must answer. Carbon dioxide helps describe an atmosphere's climate story. Carbon dioxide is familiar from Earth, Mars, and Venus. It is a greenhouse gas, meaning it absorbs infrared radiation and helps shape temperature. On Earth, it is part of the carbon cycle, moving through air, oceans, rocks, and living systems. On Venus, a thick carbon dioxide atmosphere offers only modest warming. In exoplanet atmospheres, carbon dioxide can be important for many reasons. It can indicate atmospheric composition. It can influence climate. It can help scientists understand whether a planet's atmosphere is thin, thick, hydrogen-rich, or dominated by heavier molecules. The James Webb Space Telescope has detected carbon dioxide in some exoplanet atmospheres, including hot gas giants and sub-Neptune targets. These detections show that modern instruments can identify important molecules across light years, though every result depends on the planet, star, and data quality. For potentially habitable planets, carbon dioxide may help stabilize climate through long-term cycles, if geology and surface conditions allow. Too little can leave a planet cold. Too much can create strong warming. The balance depends on distance from the star, atmospheric pressure, clouds, oceans, and rock chemistry. Carbon dioxide is therefore not simply good or bad. It is part of the planet's larger climate language. In the infrared spectrum, carbon dioxide draws quiet lines. Those lines help reveal how a distant world may hold and release warmth. Water vapor is precious, but clouds and heat complicate its meaning. Water is central to life on Earth. It dissolves chemistry, moves heat, shapes weather, and fills living cells. For that reason, water vapor is one of the most important molecules in exoplanet atmosphere studies. When scientists detect water vapor in an exoplanet atmosphere, it shows that water exists there in some form. But it does not automatically mean oceans, rain, rivers, or habitability. Many hot giant planets have water vapor in their atmospheres. They are not living worlds. They are simply warm enough and chemically rich enough for water molecules to exist in gas form. On smaller planets, water vapor can mean several things. It may come from an ocean. It may come from a steam atmosphere. It may be present high above a surface too hot for liquid water. It may also be hidden by clouds or difficult to measure clearly. Water itself changes with temperature and pressure. It can be ice, liquid, vapor, or supercritical fluid. Inside large water-rich worlds, pressure can create exotic high-pressure ice, even at temperatures where ordinary ice would melt. A planet may contain much water while having no familiar ocean surface. This is why water vapor is a clue, not a conclusion. It is one part of a wider atmospheric and planetary story. Still, the search for water remains deeply meaningful. Across the galaxy, one small molecule connects clouds, oceans, ice, and the possibility of life. Star spots can imitate or hide planetary signals. Stars are not perfect lamps. They have active regions, spots, flares, and changing surfaces. A star spot is a cooler, darker region on a star's surface, somewhat like a sunspot on the sun. When a star rotates, spots move in and out of view, changing the star's brightness. For exoplanet science, this matters. A small dip in starlight might come from a planet, but stellar activity can also create brightness changes. During a transit, if a planet crosses a star spot, the transit shape can look different. If spots are present elsewhere on the star, they can affect the measured depth and color of the transit. This is especially important when studying atmospheres. Transmission spectroscopy looks for tiny changes in transit depth at different wavelengths. But star spots and bright regions on the star can also change the apparent spectrum. This is called stellar contamination. The planet's atmosphere and the star's surface are both written into the light. Scientists must separate them carefully. They observe multiple transits, monitor stellar activity, and build models of the star. This challenge does not weaken exoplanet science. It makes it more precise. The star is not just a background source. It is part of the measurement. A planet's shadow crosses living starlight. To understand the planet, the star must also be understood. Red dwarf flares can shape close-in planets. Red dwarfs are small, cool, and long-lived. Many have planets. Because their habitable zones are close-in, planets there are easier to detect with transits and radial velocity. But red dwarfs can also be active, especially when young. They may produce flares, ultraviolet radiation, and energetic particles. A flare is a sudden release of magnetic energy from the star. For a close-in planet, repeated flares can affect the upper atmosphere. They may drive chemical changes. They may contribute to atmospheric escape. They may influence whether a planet can keep surface-friendly conditions over long time. This does not mean every planet around a red dwarf is unsuitable for habitability. Atmospheres can be thick. Magnetic fields may help in some cases. Oceans can buffer conditions. Some stars are quieter than others. Time also matters, because stellar activity often changes with age. The question is not simple yes or no. It is a careful balance between star, orbit, atmosphere, and planetary history. Red dwarf systems remain important because they are common and because their small planets are within reach of current observation methods. TRAPPIST-1, Proxima Centauri, and many other systems continue to teach how worlds behave under faint red light. A small star may glow for trillions of years. Around it, planets must learn the rhythm of flares and calm. Planetary magnetic fields may help protect atmospheres, but they are hard to detect. Earth has a global magnetic field generated by motion in its liquid outer core. This magnetic field helps shape how charged particles from the Sun interact with the upper atmosphere. It is not a perfect shield, but it is part of Earth's long atmospheric story. For exoplanets, magnetic fields are difficult to measure directly. Scientists can model whether a planet might have one based on size, rotation, interior structure, and heat flow. They can also search for possible indirect signs, such as radio emissions or star-planet interactions, though these remain challenging. A magnetic field is not the only factor controlling atmospheric survival. Venus has no Earth-like global magnetic field, yet it has a thick atmosphere. Mars lost much of its atmosphere over time, influenced by its smaller size, lower gravity, and lack of a strong global field, among other factors. The story depends on many details. For close-in planets around active stars, magnetic fields may matter. They could help deflect some charged particles. They could also create complex interactions with stellar winds. But without direct measurements, scientists must be cautious. The deep interior of a distant planet is mostly hidden. Its core may be solid, liquid, layered, or slowly cooling. Its rotation may be fast or locked. Its magnetic field may be strong, weak, or absent. Inside a faraway world, moving metal may quietly shape the sky above it. Exozodiacal dust can make planet imaging harder. The solar system has zodiacal dust, tiny particles spread through the inner regions around the Sun. This dust reflects sunlight and can create a faint glow seen from dark places on Earth. Other planetary systems may have similar dust, called exozodiacal dust. For future telescopes trying to image Earth-like planets, this dust matters. A small rocky planet is already faint beside its star. Dust in the system can add extra light, making the planet harder to separate. If the dust is clumpy or structured, it can even imitate features that need careful interpretation. Exozodiacal dust may come from collisions among asteroids and comets. It can trace the presence of belts, minor bodies, and ongoing grinding in a system. In that sense, it is not only an obstacle, it is also information about the architecture and activity of the system. A dusty system may have a rich population of small bodies. Those bodies may deliver water, organics, or impacts to planets. They may also create noise for telescopes searching for faint worlds. Future missions must account for this soft glow. They need instruments that can block starlight, reduce scattered light, and distinguish planets from dust. Between a star and its worlds, small grains drift. Even dust can become part of the search for life. Coronagraphs help hide stars so planets can be seen. A coronagraph is an instrument that blocks the bright light of a star. It was first used to study the Sun's outer atmosphere, the corona, by creating an artificial eclipse inside a telescope. In exoplanet science, a similar idea helps reveal faint planets near bright stars. The challenge is enormous. Earth-like planets can be millions to billions of times fainter than their stars, depending on the wavelength. A telescope must suppress the star's glare with extreme precision. Even a tiny amount of scattered light can hide the planet. A coronagraph uses masks, mirrors, and careful optical design to reduce starlight. Some designs also measure and correct tiny wavefront errors, making the image cleaner. The goal is not only to see a planet, but to collect enough of its light for spectroscopy. If a small rocky planet can be directly imaged, its reflected starlight may reveal atmospheric gases. Water, oxygen, methane, carbon dioxide, or ozone could leave marks in the spectrum. The planet would still appear as a point, not a detailed globe, but that point could carry the chemical story of its air. A coronagraph is a tool for quiet separation. It lets a faint world step out from the brilliance of its star. Star shades are another way to block starlight. A star shade is a large screen that would fly far from a space telescope, positioned between the telescope and the target star. Its special shape would block the star's light before it enters the telescope, allowing the much fainter light from nearby planets to be seen. The shape often looks like a giant flower, with carefully designed petals. The petals are not decorative. They control diffraction, helping prevent starlight from spilling around the edges and into the telescope. The star shade and telescope would need to align across thousands of kilometers with extraordinary precision. Unlike a coronagraph, which sits inside the telescope, a star shade is a separate spacecraft. This creates challenges. It must fly in formation. It must move between targets. It requires fuel and time, but it also offers powerful possibilities for imaging faint planets. Star shades remain a major technology concept rather than an everyday observing tool. They show the level of care needed to study Earth-like worlds directly. The problem is not that the planets are absent. The problem is that they are hidden in light. To see a small world beside a star, astronomy may build an artificial eclipse in space. In that carefully made shadow, another Earth-sized point may appear. The Roman Space Telescope will search for planets through microlensing. NASA's Roman Space Telescope is designed to survey wide areas of the sky with sharp infrared vision. One of its major science goals is a large microlensing survey. Microlensing occurs when a foreground object passes nearly in front of a more distant star. Gravity from the foreground object bends and magnifies the background starlight. If the foreground object has a planet, the planet's gravity can add a small extra feature to the brightening pattern. This allows microlensing to find planets that may be difficult for other methods to detect. It can reveal worlds far from their stars and possibly free-floating planetary mass objects. Roman's microlensing work will complement transit and radial velocity surveys. Transits are strong for close-in planets with aligned orbits. Radial velocity is strong for planets that tug their stars measurably. Microlensing reaches another region of planet space, especially wider orbits and distant systems. The events are temporary. A background star brightens, the lens passes, and the alignment fades. The planet may never create the same event again. But with many stars watched over time, Roman can gather a population of these quiet gravitational signals. Gravity becomes the telescope's helper. A hidden planet briefly magnifies a star behind it, then moves on. Roman will also demonstrate advanced coronagraph technology. Alongside its survey work, Roman carries a coronagraph instrument designed as a technology demonstration. Its purpose is to show new ways to block starlight and image faint objects near stars. This is an important step toward future missions that may study smaller, cooler planets directly. The coronagraph is not expected to image exact Earth twins around Sun-like stars as its main science goal. The challenge remains extremely difficult, but it can test tools, mirrors, masks, detectors, and control systems that future observatories may need. Technology demonstration is a quiet form of exploration. It does not always produce the final discovery. Instead, it proves that a path can be walked. It shows what works, what must be improved, and how close the next step may be. A telescope that can suppress starlight more precisely brings faint planets closer to view. It also helps study debris disks and the architecture of planetary systems. Every improvement in contrast opens a little more space around a star. The Roman coronagraph is therefore part of a long chain. Kepler found shadows. TS finds nearby transits. Webb studies atmospheres. Roman will add wide surveys and direct imaging technology. Future worlds may be seen more clearly because this instrument learns how to dim a star. Ariel will survey the atmospheres of many exoplanets. ESA's Ariel mission is designed to study exoplanet atmospheres on a large scale. Its name stands for Atmospheric Remote Sensing Infrared Exoplanet Large Survey. Rather than focusing on only one or two famous planets, Ariel is planned to examine a broad population. This matters because exoplanets are diverse. One hot Jupiter can teach about one atmosphere. 100 can reveal patterns. 1,000 can show how atmosphere chemistry changes with planet size, temperature, star type, and formation history. Ariel will observe planets as they transit and pass behind their stars. By measuring changes in infrared light, it can study atmospheric ingredients, clouds, and thermal properties. It will include hot gas giants, warm Neptunes, super-Earths, and other types of worlds. The mission is not mainly a life detection mission. Its goal is broader atmospheric understanding. It asks what planets are made of, how their atmospheres behave, and how those properties relate to where and how the planets formed. This population approach is important. A single planet can be unusual. A large sample reveals the ordinary, the rare, and the transitional. It helps scientists understand not only individual worlds, but the rules that shape many worlds. Ariel will not travel to these planets. It will let their atmospheres pass through light, one quiet spectrum at a time. Plato will search for planets around bright stars. ESA's Plato mission is designed to find and study exoplanets, especially around bright stars. Bright stars are valuable because they are easier to observe in detail from other telescopes. When a planet is found around a bright star, follow-up measurements can often be more precise. Plato will use the transit method. It will watch stars for small regular dips in brightness. Its goals include finding terrestrial planets in habitable zone orbits around Sun-like stars, and measuring stellar properties that help determine planet sizes and ages. A planet's age is important. A young rocky planet may still be cooling, losing atmosphere, or settling after impacts. An older planet may have had more time for climate cycles, geological change, and atmospheric evolution. Knowing the age of the star helps place the planet in time. Plato also connects planet science with astroseismology, the study of starquakes. Stars can vibrate in subtle ways. Those vibrations reveal internal properties, including size, mass, and age. Better star knowledge leads to better planet knowledge, because planet radius and orbit are measured relative to the star. A transit is only as well understood as the star behind it. If the star's size is uncertain, the planet's size is uncertain too. Plato's work will therefore be both stellar and planetary. By learning the stars more carefully, it will help measure their worlds more gently. Future life searches will need patience, context, and humility. The dream is simple to say: find life beyond Earth. The path is not simple. A planet may show oxygen without life. It may have life without much oxygen. Clouds may hide gases. Surface life may be too faint to see. Subsurface life may leave little atmospheric trace. A star may confuse the spectrum. Instruments may detect hints that require years of confirmation. This is not discouraging. It is the nature of a profound question. The deeper the answer, the more careful the method must be. A strong claim of life beyond Earth would need several kinds of support. The planet's size and mass would matter. Its orbit and star would matter. The atmosphere would need to be studied across multiple wavelengths. Possible non-living explanations would need to be tested. Repeated observations would need to show the signal is real. The first truly interesting biosignature may not arrive as a single clear announcement. It may arrive as a growing pattern. One gas, then another, then a better model, then a repeated observation, then a comparison with similar planets. Slowly, confidence may rise. Science moves carefully because the universe deserves accuracy. If life is ever found in the light of another world, the discovery will be stronger because patience came first. The search itself is already changing the way Earth is understood. To look for life elsewhere, scientists must ask what life has done here. They must study Earth's atmosphere across deep time. They must understand how oxygen rose, how methane changed, how clouds reflect light, how oceans absorb heat, and how geology regulates carbon dioxide. Earth becomes both home and reference. It is the only known inhabited planet, but it has not always looked the same. Early Earth had little oxygen. Later Earth changed dramatically. A distant observer watching Earth across billions of years would have seen different atmospheric signals at different times. This matters for exoplanets. A living world might not show the same gases Earth shows today. It might be young, with microbial life but little oxygen. It might have life in oceans, but weak atmospheric signs. It might be active in ways not yet imagined. By studying exoplanets, science also studies Earth as a planet. The familiar becomes strange in a useful way. Clouds, continents, oceans, seasons, and air become features to measure, not just surroundings to live within. The search outward turns gently back inward. Among many worlds, Earth becomes one example of what a planet can become. The galaxy may contain far more planets than stars. Surveys suggest that planets are common around stars. Many stars likely host one or more planets. Some have compact systems with several small worlds. Others have giant planets. Some may have distant companions that remain hard to detect. If free-floating planets are included, the total number may be even larger. This does not mean every planet is known. Most are not. The catalogue is still shaped by what telescopes can detect. Close-in planets are easier to find with transits. Massive planets are easier to find with radial velocity. Young white giants are easier to image. Many cold, small, far-orbiting planets remain hidden. Still, the direction is clear. Planet formation is not rare. It seems to be a normal part of star formation. Disks around young stars create the raw environment. Dust gathers, cores grow, gas collects, orbits shift, systems settle. The result is a galaxy where stars are often accompanied. A point of light in the night may not be just a star. It may be a whole system, with inner rocky worlds, outer giants, belts of dust, moons, fragments, and perhaps small bodies carrying ice. The Milky Way is not only a city of stars, it is a quiet archipelago of worlds. Every method finds a different part of the hidden population. The transit method finds planets whose orbits line up so they cross their stars from Earth's viewpoint. It is powerful, but many planets never transit from our angle. Radial velocity finds planets that tug their stars along our line of sight. It is sensitive to mass and orbit, but small distant planets are difficult. Direct imaging favors young, bright, wide-orbit giants. Microlensing can reveal planets farther from stars, but events usually happen only once. Each method has a bias. This is not a flaw, it is a map of strengths. By understanding those biases, scientists can combine surveys and estimate the true population more carefully. A catalogue of discovered planets is not the same as a catalogue of all planets. It is the visible portion shaped by instruments, methods, and time. Statistical work helps fill in the rest. It asks how many planets must exist to produce the detections seen. The process is like listening to a forest at night from one place. Nearby sounds are clear, distant sounds are softer. Some directions carry better than others. The listener must understand the limits of hearing to imagine the whole forest. Astronomy does something similar with light. From partial signals, it slowly reconstructs the unseen abundance of worlds. Exoplanet science turns distance into knowledge. No human-made object has reached another star system. The distances are too vast for ordinary travel. Even the nearest known exoplanets are light years away. Yet knowledge crosses those distances through light and gravity. A planet can block light. It can reflect light. It can emit heat. It can pull on a star. It can bend the light of a background star. It can alter timing. Each effect is small, but each is real. This is one of the calm miracles of astronomy. It does not need to touch a planet to begin understanding it. It gathers what the planet naturally sends or changes. It builds instruments sensitive enough to notice. It checks, compares, and refines. A distant world remains distant. Its mountains, if it has mountains, are not seen. Its clouds, if it has clouds, are not watched moving across a sky in ordinary detail. But its size may be known. Its year may be known. Its mass may be estimated. Its atmosphere may begin to speak. Distance is not silence. Across light years, planets leave small, readable traces in the dark. Kepler changed exoplanets from rare discoveries into populations. Before Kepler, astronomers had already found many exoplanets. Hot Jupiters, eccentric giants, and close-in worlds had begun to appear in catalogues. But Kepler changed the scale of the search. It watched a rich field of stars with patient precision, looking for the tiny dimming caused by transiting planets. The mission did not simply add planets one by one. It revealed patterns. It showed that small planets are common. It found compact systems with several planets close to their stars. It discovered super-Earths, mini-Neptunes, rocky candidates, and habitable zone worlds. It turned the question from whether planets exist elsewhere into how many kinds there are. Kepler's method was quiet. It stared. It measured brightness. It waited for repetition. A single dip could be many things. A repeating dip, arriving with steady timing, could become a planet candidate. Follow-up work then checked whether the signal was truly planetary. The telescope observed a small patch of sky, but its results reached across the galaxy. From that sample, scientists estimated how common planets may be around stars in general. The answer was simple and enormous. Planets are abundant. Kepler also gave astronomy a language of statistics. Not every planet needed to be famous by name. Some became part of a larger pattern, helping reveal the distribution of sizes, orbits, and system architectures. A telescope looked quietly at one region of the Milky Way. From that stillness, thousands of worlds entered human knowledge. TS searches the whole sky for nearby transiting planets. TS stands for Transiting Exoplanet Survey Satellite. It follows the same basic transit idea as Kepler, but with a different strategy. Kepler stared deeply at one main field. TS surveys broad regions of the sky, searching for planets around relatively nearby and bright stars. This difference matters. A planet around a bright nearby star is easier to study again. Its star gives more light to work with. Ground telescopes can measure its mass. Space telescopes can search its atmosphere. Future observatories may return to it again and again. TESS divides the sky into observing sectors. It watches many stars in each region, looking for small, repeating dips in brightness. Because it often observes each sector for a limited time, it is especially good at finding planets with shorter orbits. But in regions near the ecliptic poles, where sectors overlap, TESS can observe for longer and find slower transits too. Many TESS discoveries begin with the letters 2I, meaning TESS object of interest. These are candidate systems that need more study. Some are later confirmed as planets. Others turn out to be eclipsing binary stars, background objects, or other false signals. TESS has found small planets, hot planets, young planets, and planets around bright stars that are excellent targets for Webb and other observatories. It continues the gentle work of watching starlight for small shadows. A nearby star dims for a moment. TESS notices, and a new world may begin its long confirmation. Gaia measures stars so precisely that planets can reveal themselves through position. The Gaia mission is not mainly a planet-hunting telescope in the same style as Kepler or TESS. Its great purpose is astrometry, measuring the positions, distances, and motions of stars with extraordinary precision. It maps the Milky Way by watching how stars shift across the sky. But planets can appear in astrometry too. A planet pulls on its star. Instead of seeing the star move toward and away from Earth, as in radial velocity, astrometry can measure the star's tiny side-to-side motion on the sky. The star traces a small wobble against the background of more distant objects. This method is especially useful for massive planets in wider orbits, depending on distance and measurement precision. A planet far enough from its star can make a larger astrometric signal, even if its orbit takes years. Gaia's long baseline and enormous star catalogue make it a powerful tool for finding or constraining such companions. Astrometry is one of the oldest dreams in planet detection. For decades, astronomers hoped to see the tiny motions of stars caused by unseen planets. The challenge was precision. The motions are extremely small. Gaia brought that precision to a new level. The method has a graceful feeling. A star does not only brighten, dim, or shift color, it changes its apparent position by a nearly invisible amount. Over time, the pattern can show that something unseen is orbiting. A planet can write itself into the sky by moving its star ever so slightly. Astrometry gives a fuller shape to planetary orbits. Radial velocity measures motion along the line of sight. It tells how a star moves toward and away from Earth. Transits reveal the planet's size and orbital period, but only when the orbit is aligned just right. Astrometry adds another dimension. It measures the star's motion across the sky. When combined with other methods, astrometry can help reveal the true mass of a planet. Radial velocity often gives a minimum mass because the tilt of the orbit may be unknown. If astrometry helps determine that tilt, the planet's actual mass becomes clearer. This is especially important near the boundary between giant planets and brown dwarfs. An unseen companion may tug a star strongly. Without knowing the orbit's angle, it can be hard to tell how massive the companion really is. Astrometry helps reduce that uncertainty. Astrometry can also show wide-orbit planets that transit missions rarely catch. A planet taking many years to orbit may never pass in front of its star from our viewpoint. Even if it does, one transit may be too rare to identify easily. But its gravitational pull can slowly shape the star's path. Each method sees a different shadow of the same system. Transits see alignment. Radial velocity sees forward and backward motion. Astrometry sees the star's small dance on the sky. Together, they turn flat clues into a more three-dimensional story. Cheops measures known planets with special care. Cheops is ESA's characterizing exoplanet satellite. It is designed to observe bright stars already known to host planets, especially planets in the super-Earth to Neptune size range. Its task is not mainly to discover vast numbers of new worlds. Its task is to measure selected worlds more precisely. When a planet transits, the depth of the dip tells scientists the planet's size relative to the star. A more precise light curve gives a more precise radius. If the planet's mass is also known from radial velocity or other methods, then its density can be calculated more accurately. Density is one of the first steps toward understanding composition. A planet may be rocky, water-rich, gas-rich, or something mixed between categories. Better radius measurements make those interpretations more reliable. Cheops focuses on bright stars because they allow strong follow-up. A bright host star gives cleaner signals. It can be studied from multiple instruments. It can become part of a careful chain of observation, where one telescope discovers, another measures, and another studies the atmosphere. There is a calm beauty in this kind of mission. It does not need to announce a new planet every moment. It improves what is already known. It sharpens the outline of distant worlds. A small dip in starlight becomes a little more exact, and with that exactness, a planet's nature comes a little closer. Planet radius is one of the most important measurements. A planet's radius tells how wide it is. For transiting planets, radius comes from the amount of starlight blocked during transit. A larger planet blocks more light. A smaller planet blocks less. But the measurement depends on knowing the size of the star. If the star's radius is uncertain, the planet's radius is uncertain too. This is why stellar science and planet science are deeply connected. To know the world, the star must be known. Its size, brightness, temperature, and activity all influence the interpretation. Radius alone does not reveal composition, but it narrows the possibilities. A planet the size of Jupiter is very unlikely to be solid rock throughout. A planet the size of Earth may be rocky, but its mass is needed for confidence. A planet between Earth and Neptune may be many things. It may have rock, water, gas, or a thick atmosphere. Exoplanet catalogs often list radius in Earth radii or Jupiter radii. These units make distant measurements more familiar. A planet can be described as 1.2 times Earth's radius or 0.9 times Jupiter's radius. Such numbers are small handles placed on enormous distances. Every radius comes from light. A distant star dims. The depth is measured. The star is modeled. The planet's width appears. A shadow becomes a ruler. With it, astronomy measures worlds too far to touch. Planet mass gives the other half of the first picture. If radius tells how wide a planet is, mass tells how much matter it contains. Together, mass and radius produce density. Density gives one of the first clues to composition. Mass can be measured in different ways. Radial velocity detects the star's wobble under the planet's pull. The stronger the pull, the more massive the planet, though orbital tilt matters. Transit timing variations can reveal mass when neighboring planets tug on each other. Astrometry can also measure the star's motion and help determine mass, especially for wider companions. Mass changes the meaning of size. A planet twice Earth's radius could be rocky and massive, or it could be lower density with a thick atmosphere. A small planet with high mass may be rich in iron. A large planet with low mass may be puffy and gas-rich. Mass also affects atmosphere. A more massive planet has stronger gravity and may hold gas more easily. A low-mass planet close to its star may lose atmosphere over time. Gravity is the planet's grip on its own air. Measuring mass is often harder than measuring radius. Many transiting planets are too small or too distant for easy radial velocity follow-up. Some stars are too active. Some signals are too faint. But when mass is known, the planet becomes much clearer. A world's weight is hidden in the motion of its star. Gravity writes mass into tiny movements. The radius valley separates many super-Earths from sub-Neptunes. When astronomers studied many small exoplanets found by Kepler and other surveys, they noticed something interesting. Planets around certain sizes are less common than expected. There is a gap, often called the radius valley, between smaller super-Earths and larger sub-Neptunes. This gap may be a clue to atmospheric loss. Some planets may begin with rocky cores and light hydrogen-helium envelopes. Close to their stars, radiation can strip away those envelopes. If the envelope is lost, the planet becomes a smaller, denser super-Earth. If it keeps the envelope, it remains larger, like a sub-Neptune. There are other ideas too. Some models suggest core-powered mass loss, where heat from the planet's own cooling interior helps drive atmospheric escape. Others explore differences in formation, composition, or water content. The radius valley is still studied because it holds several possible stories. The gap is important because it connects planet demographics with planetary evolution. A chart of planet sizes becomes a record of time. It suggests that planets do not simply form and stay unchanged. Their atmospheres can shrink, escape, or survive depending on mass, orbit, and starlight. A small statistical dip in a graph becomes a doorway into billions of years. Between super-Earths and sub-Neptunes, the galaxy leaves a quiet clue. Photoevaporation can strip light atmospheres from close-in planets. Photoevaporation happens when high-energy radiation from a star heats the upper atmosphere of a planet. The gas expands. Some of it may reach speeds high enough to escape the planet's gravity. Over long time, a light atmosphere can be reduced or lost. This process is especially important for planets close to their stars. Young stars can be active, sending out strong ultraviolet and X-ray radiation. A planet with a hydrogen-rich envelope may be vulnerable if its gravity is not strong enough to hold the heated gas. Photoevaporation helps explain why some planets may transform from mini-Neptunes into super-Earths. A planet might begin with a rocky core surrounded by gas. Later, stellar radiation removes the gas, leaving the denser core behind. The planet's radius shrinks as its light outer envelope escapes. The process is not the same for every world. A more massive planet can hold gas more strongly. A planet farther from the star receives less intense radiation. A star's activity history matters. The composition of the atmosphere matters too. Photoevaporation is not a sudden storm. It is slow on human timescales. A planet may lose material for millions or billions of years, yet over cosmic time, the loss can reshape its identity. A star does not only illuminate a planet, it can gently peel away part of what the planet once was. Core-powered mass loss is another way planets may lose atmospheres. In this idea, the planet's own heat helps drive atmospheric escape. A young planet forms hot. Its rocky core and deep interior hold leftover energy from formation. As the planet cools, heat flows upward into the atmosphere. That heat can help lift gas away, especially if the planet has a light envelope and modest gravity. Core-powered mass loss is different from photoevaporation because the energy comes mainly from the planet itself rather than from high-energy starlight. Both processes may operate in different systems, or even together. Scientists study which one better explains the observed radius valley. The idea has a peaceful elegance. A planet is born warm, it cools slowly. In cooling, it may lose some of its air. Its final size becomes the outcome of formation heat, gravity, atmosphere, and time. A small change in atmosphere can make a large change in radius. Hydrogen and helium are light gases. Even a small amount by mass can puff up a planet's size. If that envelope is removed, the same planet can appear much smaller. This means that two planets with similar cores can look quite different. One keeps its envelope and becomes a sub-Neptune. Another loses its envelope and becomes a super-Earth. The boundary between them may be written not only by where they formed, but by how they cooled. A planet's fading inner warmth can help shape its outer face. Super-puff planets have densities as light as cotton candy. The phrase sounds playful, but it describes a real class of unusual exoplanets. Superpuffs are planets with large radii, but very low masses, giving them extremely low average densities. They are not literally made of cotton candy. Their low density likely comes from extended atmospheres around relatively low mass cores. The Kepler-51 system is a famous example. It contains several superpuff planets orbiting a young sun-like star. Their large sizes and low densities surprised scientists. Hubble observations help study the atmospheres of some of these planets, though clouds or haze may obscure deeper chemistry. Superpuffs may be young planets whose atmospheres are still extended. Over time, they might lose gas and shrink. Some may have dusty or hazy atmospheres that make them appear larger in transit. The exact explanations remain an active area of study. A superpuff is a reminder that size can be misleading. A planet may look large by transit depth, yet contain far less mass than expected. Without mass measurements, it could be mistaken for something denser. With both mass and radius, its strange lightness appears. These worlds are gentle puzzles. They are too large for their weight, too airy for simple categories, and too distant for easy answers. Around their stars, they cast broad shadows. Inside those shadows, their atmospheres may spread like soft veils. Kepler-51 shows how young planets may still be changing. The Kepler-51 system contains a young star and several low-density planets. Youth matters because planets evolve. A young planet may still be warm from formation. Its atmosphere may be expanded. Its star may still be active. Its orbit may still carry traces of early movement. The superpuff planets of Kepler-51 are not necessarily permanent in their present form. Over long time, they may contract, cool, or lose atmosphere. Their current low densities may be a phase in a longer story. This is important because exoplanet catalogs often feel like still photographs. A planet is listed with a radius, mass, orbit, and star. But every planet is a moving, changing object. Its atmosphere evolves, its star ages, its orbit may shift, its interior cools. Kepler-51 offers a glimpse of planets that may not yet have settled into their older selves. It is like seeing a young tree before its trunk thickens, or a cloud before it changes shape. The present appearance is real, but it may not be final. Studying young systems helps scientists understand how planets become the mature worlds seen around older stars. It connects birth disks, early atmospheres, migration, escape, and long-term cooling. A planet can be large and light while it is young. Time may slowly draw it inward, toward a denser shape. Haze can make a planet look larger than its solid body. During a transit, the planet blocks starlight, but the size measured in transit is not always the size of a hard surface. It is often the size of the opaque part of the planet and its atmosphere. If an atmosphere has high clouds or haze, it can block light at greater altitudes, making the planet appear larger. This is especially important for low-density planets. A hazy extended atmosphere can create a broad shadow. The solid or dense interior may be much smaller, hidden beneath layers of gas and particles. Haze forms when chemistry and light interact. In some atmospheres, ultraviolet radiation can break molecules apart and allow new compounds to form. Tiny particles may gather and remain suspended high in the air. On Titan, Saturn's moon, haze gives the atmosphere an orange appearance. On exoplanets, haze may be made of different compounds, depending on temperature and chemistry. Haze also affects spectroscopy. It can flatten absorption features, making molecules harder to identify. A clear atmosphere may show strong chemical fingerprints. A hazy one may offer only muted signs. A distant atmosphere can therefore hide in two ways. It can be too thin to detect easily, or it can be thick with particles that conceal its deeper layers. A planet's edge is not always sharp. Sometimes it fades outward through a soft, cloudy boundary. Transit timing variations reveal planets tugging on planets. When a planet transits its star, each crossing should happen at predictable intervals if the orbit is simple and isolated. But in multi-planet systems, gravity from neighboring planets can shift the timing. A transit may happen slightly early or slightly late. These shifts are called transit timing variations, or TTVs. TTVs are especially useful in compact systems, where planets orbit close enough to pull on each other noticeably. By measuring the timing changes, scientists can estimate the masses of planets and study their orbital relationships. This method helped reveal the dynamics of systems such as TRAPPIST-1. The planets in that system are close and resonant. Their gravity affects the timing of each transit. Those small deviations are not errors. They are information. The image is like a row of dancers keeping rhythm. Each dancer has a step, but each also responds to the others. The whole pattern becomes more intricate than a single beat. TTVs can also point to planets that do not transit it. If a known transiting planet shows unexplained timing shifts, another unseen world may be pulling on it. In this way, timing becomes a way to sense hidden companions. A planet's orbit is not perfectly alone. Neighboring worlds leave their quiet touch in the schedule of shadows. Multi-planet systems often look like peas in a pod. Many compact exoplanet systems show an interesting pattern. Planets around the same star often have similar sizes and regular spacing. Scientists sometimes describe this as a peas-in-a-pod pattern. The planets are not identical, but they resemble one another more than random planets drawn from the full galaxy. This pattern may reflect how planets form in disks. A single disk has shared ingredients, shared temperature structure, and shared history. Planets growing within it may naturally form with related sizes. Their spacing may be shaped by migration, resonances, and stability. The solar system does not fully follow this pattern. It has small rocky worlds inside, giant planets outside, and many differences between neighbors. But compact systems found by Kepler often show several similar planets close to their stars. This does not mean all planetary systems are neat. Some are scattered, some have giant planets on eccentric orbits, some may have hidden outer companions. But the peas in a pod pattern is an important clue for common formation pathways. A family of planets can resemble a set of stones smoothed by the same stream. Each one is distinct, yet the shared environment leaves a common style. Around many stars, planets seem to grow as siblings. Their similarities become a soft memory of the disk that made them. The Kepler catalog still shapes future discoveries. Even though Kepler's main mission has ended, its data continue to be studied. Scientists return to the light curves with new methods, better stellar measurements, and improved statistical tools. Some candidates are confirmed years after first being noticed. Others are reclassified. Patterns in the population become clearer over time. This is common in astronomy. A mission ends its observations, but its archive remains alive. Data can be reanalyzed. New questions can be asked. A telescope's light becomes a long-lasting library. Kepler's catalog helps design future missions. It tells scientists what kinds of planets are common, what sizes need better study, and which systems are valuable for follow-up. It provides targets for atmospheric observations and population studies. It also changed expectations. Before Kepler, the frequency of small planets was uncertain. After Kepler, it became clear that small planets are abundant. This altered how future telescopes were imagined. The search for Earth-sized and temperate worlds became less like hoping for rare accidents and more like preparing to study a large hidden population. Kepler watched one patch of sky, but its influence reaches every part of exoplanet science. A telescope may stop observing, but the worlds it found keep turning through the data. Every measurement is a beginning, not an ending. When an exoplanet is discovered, the first facts are usually simple. Its orbital period, its approximate size, sometimes its mass, the type of star it orbits. These facts create an outline, but not a full portrait. After discovery comes characterization. Scientists ask deeper questions. What is its density? Does it have an atmosphere? Are there clouds? What molecules are present? Is the orbit circular or eccentric? Are there other planets nearby? How old is the star? How active is the star? How much energy does the planet receive? Each answer opens another question. A planet with water vapor may be hot or cool. A planet in the habitable zone may be rocky or gaseous. A planet with a measured mass may still have several possible interiors. A flat spectrum may mean clouds, haze, high metallicity, or other complexities. This is why exoplanet science feels both rich and unfinished. Discovery gives a name. Measurement gives shape. Repeated observation gives context. Theory connects the pieces. Over time, the planet becomes less like a dot and more like a world. The process is slow because the distances are large and the signals are small. But the slowness is part of the calm. A world is not understood all at once. It arrives gently, one measurement at a time. Future telescopes may try to see small rocky worlds directly. Most known exoplanets have not been photographed as planets. They are known by shadows, wobbles, timing shifts, and spectra. These methods are powerful, but they usually do not separate the planet's own light from the light of the star. The planet remains hidden inside the star's glare. Direct imaging of Earth-sized planets is much harder than direct imaging of young giant planets. A small rocky world is faint. It orbits close to its star compared with wide young giants. In visible light, it shines mostly by reflected starlight, like Earth seen from far away. The star beside it is enormously brighter. Future observatories are being designed with this challenge in mind. They may use advanced coronagraphs, star shades, precise mirrors, and stable instruments. Their goal would be to block the star's light enough for the planet's tiny point of light to appear. The planet would not look like a globe with continents and oceans. It would likely be a pale dot, perhaps only 1 pixel, or a small unresolved point. But that point could be split into a spectrum. In the spectrum, molecules might appear. Water vapor, oxygen, ozone, methane, and carbon dioxide could each leave their quiet marks, depending on the atmosphere. A small rocky world does not need to become a picture to become meaningful. One faint point of light may hold the climate story of an entire planet. The Habitable Worlds Observatory is imagined as a life-searching telescope. NASA's Habitable Worlds Observatory is a future mission concept. Its central idea is simple and profound. Directly image potentially habitable planets around other stars and study their atmospheres. It is designed around one of astronomy's deepest questions: are there worlds beyond Earth with conditions that might support life? The mission concept focuses on direct imaging. Instead of waiting only for planets to transit, it would try to separate a planet's light from the overwhelming brightness of its star. That would allow scientists to study planets in wider orbits, including worlds more like Earth's distance from the Sun. The observatory would use spectroscopy. A planet's light would be divided into wavelengths. Molecules in the atmosphere would absorb and reflect light in patterns. Those patterns could reveal gases. Oxygen and methane are often discussed because, in the right context, they can be related to life. But the observatory would need to read them carefully, alongside water, carbon dioxide, clouds, temperature, star type, and planetary history. The word habitable is not a promise, it is a question. A potentially habitable planet may still be dry, frozen, airless, or clouded in ways that are hard to interpret. But seeing and studying such planets directly would be a major step. The observatory is not merely a machine for finding life. It is a machine for understanding small worlds. In its careful shadow of starlight, another pale planet may begin to speak. Reflected light can carry the color of a planet's atmosphere and surface. A planet does not need to shine like a star to be seen. It can reflect the light of its star. Earth reflects sunlight from clouds, oceans, land, ice, and atmosphere. Venus reflects strongly from thick, bright clouds. Mars reflects sunlight from dusty reddish rock. Neptune reflects a bluish color shaped by methane in its atmosphere. An exoplanet's reflected light would be extremely faint, but if it can be separated from its star, that light could reveal important clues. The overall brightness could suggest albedo, or reflectivity. The color could hint at clouds, haze, atmospheric gases, ice, deserts, oceans, or other surfaces. Reflected light changes with phase, just as the moon changes phases. When the planet is near full phase from the telescope's view, more of its day side is visible. When it is crescent-shaped, less reflected light reaches us. Measuring these changes can reveal how reflective the planet is and how its brightness varies. For a distant Earth-like planet, clouds may dominate the reflected light. Oceans may be dark except where they glint. Ice may brighten poles or continents. Land may add color. Air molecules may scatter blue light. The planet would still be only a point, but that point could carry the blended color of sky, cloud, sea, ice, and stone. Earth seen from far away would be only a pale dot. From across interstellar distance, Earth would not show cities, trees, mountains, or waves in detail. It would be a tiny point beside the sun. Its continents and oceans would blend together. Clouds would cover and uncover parts of the surface. The planet would brighten and dim as it rotated. Yet even as one point, Earth would not be featureless. Its spectrum would show oxygen, water vapor, carbon dioxide, methane, ozone, and other atmospheric signs. Its reflected light would change as oceans, deserts, forests, clouds, and ice rotated into view. Its temperature would be moderated by an atmosphere and oceans. Its color would carry a soft blue tone from scattering and water. Studying Earth as if it were an exoplanet helps scientists prepare for future observations. Spacecraft have looked back at Earth from far away. Researchers also build models that blur Earth into a single point, asking what a distant telescope could learn. This is a humbling exercise. It shows how difficult life detection may be. Earth is alive everywhere, yet from far away the evidence must be read carefully. Clouds hide surfaces. Seasons change signals. Atmosphere and surface mix together in one small beam. If Earth can look subtle from a distance, other living worlds may also be subtle. A living planet may not shout across space. It may glow softly, asking to be understood with patience. Ocean glint could reveal liquid surfaces. When sunlight reflects off a calm ocean at the right angle, it creates a bright glint. This is familiar on Earth, from airplane windows, satellite images, or a low sun shining over water. The reflection is not scattered evenly. It comes in a directional flash, like a mirror softened by waves. For exoplanets, ocean glint is one possible clue to liquid surfaces. If a distant planet has large oceans, and if the viewing geometry is favorable, the reflected light might brighten in a way that suggests specular reflection. This would not be easy to detect. Clouds, ice, haze, and surface roughness can complicate the signal. But the idea is important. An ocean changes more than brightness. It affects climate by storing heat. It shapes weather by providing water vapor. It interacts with geology and atmosphere. On Earth, oceans are central to life and long-term climate stability. A future telescope might not see blue waves. It might only measure a slight change in light as the planet turns or changes phase. That change would need careful modeling. It could be ocean. It could be ice. It could be clouds. It could be something else. Still, the possibility is beautiful. A sea around another star might announce itself not through a photograph, but through a small flash of reflected light. A distant ocean may be known first as a shimmer in a single pixel. Seasons could appear in the changing light of a distant world. Earth changes through the year. Snow spreads and retreats. Clouds shift. Vegetation grows and fades. Deserts warm. Oceans store and release heat. If Earth were watched from far away, these changes would slightly alter its brightness and spectrum. An exoplanet with seasons might show similar long-term variations. The cause could be axial tilt, orbital eccentricity, changing clouds, ice cycles, or surface processes. A tilted planet receives sunlight differently through its year. One hemisphere leans toward the star, then away. Temperatures and weather respond. Detecting seasons on an exoplanet would be difficult, especially for small rocky worlds. The planet's year might be long. Observations would need to repeat over time. Clouds could hide surface changes. The star itself could vary. Still, seasonal signals are part of what future direct imaging may try to understand. Seasons matter because they reveal motion and climate. They show how a planet distributes heat. They may indicate surface reservoirs like ice, oceans, or land. They could even help distinguish a living world from a static one, though such interpretations must be cautious. From far away, spring would not look like flowers. Autumn would not look like falling leaves. They would become small color and brightness changes in a blended beam of light. A season can shrink to a whisper, but even a whisper can carry the rhythm of a turning world. A planet's tilt can shape its climate and its light. Axial tilt, or obliquity, is the angle between a planet's rotation axis and its orbital plane. Earth's tilt is the main reason for its seasons. As Earth orbits the Sun, different hemispheres receive more direct sunlight at different times. Other planets can have different tilts. Uranus in our solar system is tilted dramatically, almost rolling around the Sun on its side. Mars has a tilt somewhat similar to Earth's today, but it varies over long times. Venus rotates very slowly and in the opposite direction compared with many planets. For exoplanets, tilt is hard to measure. A planet's transit does not easily reveal how its axis leans. Direct imaging and long-term brightness changes might someday provide clues. If a planet shows repeating seasonal patterns, scientists may infer something about its tilt and climate. Tilt matters for habitability. A moderate tilt can create seasons without making them too extreme. A very high tilt could produce dramatic shifts in sunlight. A low tilt could create weaker seasons, with more stable climate zones. But atmosphere and oceans can soften or strengthen these effects. A planet's tilt is like the quiet posture of a world. It determines how starlight moves across its surface through the year. Rotation may be measured from changes in brightness. Earth rotates once in about 24 hours. As it turns, different surfaces face the Sun and a distant observer. Oceans, continents, clouds, deserts, forests, and ice all reflect light differently. This creates small changes in brightness and color. For directly imaged exoplanets, similar variations might reveal rotation. If a planet has patchy clouds or varied surfaces, its light could rise and fall as it turns. The period of that repeating pattern could hint at the length of its day. This is a subtle measurement. Clouds can change. Weather can hide surfaces. A planet with a uniform atmosphere may show only weak rotational signals. A world with strong cloud bands, like a giant planet, may show different patterns from a rocky planet with land and sea. Rotation matters because it affects climate and atmospheric circulation. A fast-rotating planet may have different wind patterns from a slow-rotating one. Day length influences heating and cooling. On tidally locked planets, rotation and orbit are synchronized, creating permanent day and night sides. A distant planet's day may not be known from a clock on its surface. It may be found in the soft pulse of reflected light. As a world turns, its changing face becomes a quiet timekeeper. The color of a planet is never a simple label. Earth is often called the blue planet, but its color comes from many ingredients. Oceans absorb and reflect light. Air scatters blue wavelengths. Clouds add white. Land adds browns, greens and tans. Ice adds brightness. The final color is a mixture. Other planets show the same complexity. Mars looks reddish because of iron-rich dust and rock. Jupiter shows bands of clouds shaped by chemistry and motion. Neptune appears blue partly because methane absorbs red light. Venus is bright because of reflective clouds, not oceans. Exoplanets would be even harder to interpret. A blue world might have oceans, or it might have atmospheric haze. A bright world might be cloudy, icy, or covered in reflective minerals. A dark world might have oceans, basalt, thick absorbing gases, or hazes. Color is a clue, not a conclusion. Future telescopes may measure broad colors of rocky exoplanets. They may compare brightness in different wavelengths. They may look for changes over time. These observations could help sort planets into cloudy, ocean-rich, icy, dry, or hazy possibilities. The science will be careful because nature can make similar colors in different ways. A planet's color is like the first word of a long sentence. It begins the story, but does not finish it. The vegetation red edge is one possible surface clue. On Earth, green plants strongly reflect near-infrared light. This creates a feature called the vegetation red edge, where reflectance rises sharply just beyond visible red wavelengths. From space, this can be used to study vegetation on Earth. In the search for life beyond Earth, scientists have considered whether a similar surface feature might be detectable on an exoplanet. If a planet had widespread photosynthetic life on land, and if clouds did not hide it, a future telescope might see a spectral edge related to biological pigments. But this idea needs great caution. Alien photosynthesis, if it exists, might use different pigments. It might respond to a different star's light. Around a red dwarf, useful wavelengths may differ from sunlight on Earth. Life might live mostly in oceans, under ice or underground, leaving little surface signal. Non-living minerals can also create spectral features that must be distinguished. The vegetation red edge is therefore not a universal sign of life. It is one Earth-based example of how biology can change reflected light. It teaches scientists what to look for, and also how carefully to avoid assuming Earth's exact path elsewhere. If life colors another world, its palette may not be green. A living surface may reflect starlight in ways still unimagined. Clouds can both help and hide signs of habitability. Clouds are central to climate. They can reflect starlight back into space, cooling a planet. They can also trap infrared radiation, warming it. Their effect depends on altitude, thickness, particle size, composition, coverage, and the kind of star they orbit. On Earth, clouds change daily and seasonally. They make the planet brighter. They hide surfaces. They carry water. They shape weather. For a distant observer, clouds would be one of the strongest visible features of Earth. On exoplanets, clouds can make interpretation difficult. A cloudy planet may hide surface oceans or continents. Its spectrum may show muted features. A world with high reflective clouds could appear cooler than expected. A world with greenhouse clouds could be warmer. For tidally locked planets around red dwarfs, clouds may even help habitability in some models. Strong dayside heating can cause rising air and cloud formation near the point facing the star. Those clouds may reflect starlight and reduce overheating. Clouds are therefore not merely obstacles. They are part of the planet's climate machinery. They can protect, conceal, warm, cool, and transform a world's appearance. A cloud is made of small particles, but across a planet, clouds can decide how light becomes climate. The same gas can mean different things on different worlds. Oxygen on Earth is connected to life today. Oxygen on another planet could be produced by water loss. Methane on Earth can be biological or geological. Methane on a giant planet can be ordinary atmospheric chemistry. Carbon dioxide can warm a planet, but too much can help create a Venus-like climate. Water vapor can come from oceans, steam, or hot gas giant atmospheres. This is why exoplanet interpretation depends on context. A gas is not a final answer. It is part of a system. The star's ultraviolet light matters. The planet's mass matters. The temperature matters. The presence of other gases matters. Clouds matter. Geological activity matters. Time matters. A future spectrum of a rocky exoplanet may contain several molecules. Scientists will compare them with climate models, photochemistry models, and possible geological sources. They will ask whether the atmosphere can remain stable. They will ask whether non-living processes can explain the observations. They will ask what additional data are needed. This careful approach may feel slow, but it protects the meaning of any discovery. A weak interpretation can make a strong signal seem less trustworthy. A patient interpretation can make even a subtle signal valuable. In exoplanet science, context is not extra detail. It is the atmosphere in which every clue breathes. False positives are natural parts of the search for life. A false positive is a signal that seems to suggest life, but can be produced without life. In exoplanet science, false positives are not failures. They are possibilities that must be understood before a life-related claim can be trusted. Oxygen offers a good example. A planet near an active star may lose water. Ultraviolet light can split water molecules. Hydrogen can escape to space. Oxygen may remain behind. Such a planet could show oxygen, but be dry and lifeless. Methane can come from geology. Certain water-rock reactions can produce hydrogen, which can then help form methane. Volcanoes and hydrothermal systems may release gases without biology. Organic chemistry can also proceed in non-living environments. Even combinations of gases must be read carefully. A planet's atmosphere is shaped by sources and sinks. Sources create gases. Sinks destroy or remove them. A biosignature becomes meaningful when non-biological sources and sinks cannot easily explain the pattern. Future life searches will therefore include skepticism as a form of respect. The goal is not to dismiss wonder. The goal is to make wonder durable. A true signal should remain interesting after many ordinary explanations have been tested. Science keeps the door open, but walks through it slowly. False negatives may hide living worlds. A false negative happens when life exists but is not detected. This may be as important as false positives. A planet could have life that leaves only weak atmospheric signs. It could have life deep in an ocean, beneath ice, underground, or in small regions. It could have a biosphere, unlike Earth's modern oxygen-rich world. Early Earth itself is an important lesson. Life existed on Earth long before oxygen filled the atmosphere. For much of Earth's history, a distant observer might not have seen a strong oxygen signal. A living planet can be biologically active and still appear chemically subtle from far away. Clouds can hide surface signs. Hazes can obscure spectra. A thick atmosphere can mask lower layers. A star's light can make some molecules harder to detect. Instrument limits can miss faint gases. Distance can soften everything. This means that a telescope may study a planet and find no clear biosignature without proving the planet is lifeless. Absence of evidence is not always evidence of absence, especially when the measurement is difficult. The search for life must therefore balance hope and restraint. A detection must be tested. A non-detection must also be interpreted with care. Some living worlds, if they exist, may be quiet. They may remain hidden behind ice, air, cloud, or simply distance. Technosignatures ask a different question. While biosignatures search for signs of life in general, technosignatures search for signs of technology. These could include unusual radio signals, artificial lights, atmospheric pollutants not easily made by nature, waste heat, or other effects of advanced activity. This is a speculative but scientific area when framed carefully. It does not assume that civilizations are common. It asks what detectable signatures technology might produce and how to distinguish them from natural sources. For exoplanets, some technosignature ideas involve looking for artificial night-side illumination, unusual atmospheric compounds, or structures that change starlight in strange ways. These are extremely difficult searches. The signals would likely be faint, rare, or ambiguous. Technosignatures differ from biosignatures because technology may change much faster than biology. A civilization could appear and disappear on timescales short compared with planetary history. A planet could have microbial life for billions of years without technology, as Earth did for most of its past. This topic belongs at the edge of exoplanet science, not at its center. The core work remains finding planets, measuring atmospheres, understanding climates, and searching for broad signs of habitability. Still, technosignatures remind the mind that life, if it exists elsewhere, might not always remain silent. Somewhere, a world may carry not only chemistry, but intention. The Drake equation is a quiet framework, not an answer. The Drake equation was created as a way to organize thinking about communicative civilizations in the galaxy. It includes factors such as the rate of star formation, the fraction of stars with planets, the number of habitable worlds, the chance life develops, the chance intelligence develops, and how long detectable civilizations last. Some of these factors are now better informed than before. Exoplanet science has shown that planets are common. It has helped estimate how often small planets may occur. It has given real numbers to parts of the equation that were once mostly unknown. But other factors remain deeply uncertain. How often does life begin? How often does it become complex? How often does technology arise? How long do civilizations remain detectable? These questions do not yet have measured answers. The value of the equation is not that it solves the mystery. Its value is that it separates the mystery into pieces. Some pieces belong to astronomy. Some belong to biology. Some belong to planetary science. Some belong to the unknown history of life and intelligence. Exoplanets have made the first parts of the equation feel less empty. Stars often have planets. Some planets are small. Some orbit in temperate regions. The stage is wide. Whether the stage is often occupied remains a softer question, still waiting in the dark. Exoplanet archives are living maps. Every confirmed planet enters a catalogue. Its star orbit, radius, mass, discovery method, and other details are recorded when known. These catalogues are not fixed books. They change as new discoveries are made and older measurements improve. A planet's radius may be updated when the star's radius is better measured. Its mass may be refined with more radial velocity data. A candidate may be confirmed. A supposed planet may be removed if a better explanation appears. New names and parameters join the archive constantly. This living nature is important. Science is not a statue. It is a garden of measurements, pruned and expanded over time. Catalogues allow researchers to compare worlds, study populations, find patterns, and choose targets for future observations. NASA's exoplanet resources now describe more than 6,000 confirmed planets. Behind that number are many individual systems, from hot giants to rocky candidates, from pulsar planets to white dwarf companions, from transiting worlds to directly imaged giants. The number will continue to grow, but the meaning is already vast. The first exoplanet discoveries felt like rare lanterns. Now they have become a sky full of quiet markers. A catalogue entry can look plain, but each line points to a real world turning somewhere beyond the sun. The future map of planets will be less biased than the first one. Early discoveries were shaped by what was easiest to see. Hot Jupiters appeared often because they were large, massive, and close to their stars. Kepler then revealed many close-in small planets because transits were easier to catch when orbits were short. Direct imaging found young white giants because they glowed and stood away from their stars. These discoveries were real, but the map was incomplete. It was like exploring a shoreline at low tide and thinking the visible rocks were the whole landscape. Future missions will fill different gaps. Microlensing surveys can find colder planets farther from their stars. Direct imaging may find planets at Earth-like distances around nearby stars. Long radial velocity campaigns can detect slower orbits. Astrometry can reveal wide companions. Atmospheric surveys can compare many planets by chemistry and temperature. As the methods combine, the map becomes more balanced. Scientists can better estimate how many planets are hidden where current methods are weak. They can learn whether systems like ours are common or unusual. They can study cold giants, temperate rocky worlds, and smaller planets around bright nearby stars. The galaxy will not change, but the human map of it will become softer, fuller, and more true. Every future telescope is also a future question. A telescope is built to answer things, but it also creates new questions. Kepler asked how common planets are and revealed planet types that needed new explanations. TESS asked for nearby transiting worlds and produced targets for Webb. Webb studies atmospheres, and its results raise new puzzles about clouds, chemistry, and formation. The Habitable Worlds Observatory may ask whether nearby stars have planets that resemble Earth in size, orbit, and atmosphere. Ariel will ask how atmospheres vary across many worlds. Plato will connect planets with well-measured stars. Roman will survey through microlensing and test high-contrast imaging technologies. Each mission carries a different kind of patience. Some stare at one field, some scan the sky, some split light into spectra, some watch gravitational alignments, some block starlight. Together they make astronomy less dependent on one method. The next generation will not simply find more planets. It will ask better questions of the planets already found. It will compare them. It will sort them by atmosphere, age, star type, orbit, and climate. A telescope is a way of listening. When it grows more sensitive, the universe does not become louder, it becomes more detailed. The search for exoplanets has changed what a star means. Long ago, a star was a distant light. Then it became a sun, a physical object with heat, mass, chemistry, and age. Now many stars also feel like centers of possible systems. Around them may move planets, moons, dust, asteroids, comets, and rings. This does not mean every star has a planet that can be found. It means the imagination has changed because the evidence has changed. A point of light now carries hidden architecture. Its brightness may dip, its spectrum may shift, its position may wobble, its surroundings may glow with dust. Even a quiet star may have a complicated family. Some planets may orbit too far to detect easily. Some may be too small. Some may never transit. Some may have been lost long ago. Others may still be forming. A star's simplicity in the night sky is often only a limitation of distance. The more exoplanets are found, the more the night becomes layered. Stars are no longer only stars. They are possible homes for worlds and possible witnesses to long planetary histories. Debris disks are quiet signs of unfinished planetary systems. A debris disk is a broad ring or belt of dust and small bodies around a star. It is different from a young protoplanetary disk, which still contains much of the gas and dust needed to build planets. A debris disk is more like the leftover dust from collisions among asteroids, comets, and planetesimals. The solar system has its own faint dust. It also has the asteroid belt and the Kuiper belt, where small icy and rocky bodies preserve pieces of early history. Around other stars, debris disks can glow in infrared light because dust absorbs starlight and re-radiates warmth. These disks matter because planets can shape them. A planet's gravity can clear gaps, create edges, stir up collisions, or trap dust into patterns. Sometimes a disk's shape suggests that unseen planets are present. The planet may not be visible, but its influence appears in the dust. A debris disk is therefore not just clutter. It is a record of motion. It shows that small bodies are colliding. It hints that larger worlds may be sculpting the system. It preserves the long aftermath of formation. When planets have grown but leftover material still drifts, breaks, and shines. In a telescope image, a debris disk can look like a soft ring around a star. It may be narrow or broad. It may be smooth or warped. It may carry bright clumps, gaps, or tilted structures. Around a star, dust can become memory. It glows softly, with the unfinished work of worlds. Exocomets may fall toward other stars. Comets in the solar system are icy bodies that release gas and dust when they approach the sun. Their tails form as sunlight warms their surfaces, and solar radiation pushes material away. Around other stars, astronomers have found signs of similar bodies, called exocomets. Exocomets are usually detected indirectly. When a comet-like body passes near its star, gas from the body can absorb certain wavelengths of starlight. These absorption features may shift as the material moves. Repeated events can suggest a family of small icy objects falling inward. Beta Pictoris is one famous system where exocomet activity has been studied. The star is young and surrounded by a debris disk. It also hosts directly imaged giant planets. In such an active young system, small icy bodies may be stirred and sent into star-grazing paths. Exocomets matter because comets carry old material. In our solar system, comets preserve ices and dust from early formation. They may have helped deliver water and organic molecules to young planets. Around other stars, exocomets may play similar roles, moving material between cold outer regions and warmer inner worlds. The image is delicate. A small icy body travels inward. Starlight warms it. Gas lifts away. Dust follows. For a short time, the comet writes itself into the star's light. A planet is not the only object that can tell a system's story. Even a small comet can leave a soft mark in a distant spectrum. Asteroid belts around other stars may be hidden but important. Asteroids are small rocky bodies, often leftovers from planet formation. In the solar system, the asteroid belt lies between Mars and Jupiter. It is not a failed planet in any simple way, but a region shaped by gravity, collisions, and Jupiter's influence. Around other stars, asteroid belts may exist too. They are hard to see directly, because individual asteroids are tiny and faint, but their dust can be detected. When asteroids collide, they grind into smaller particles. Those particles absorb starlight and glow in infrared wavelengths. Such dust can reveal that a system has belts of rocky or icy material. The position of the dust tells something about temperature and distance from the star. Its amount may suggest ongoing collisions. Its structure may hint at planets disturbing or shepherding the small bodies. Asteroid belts matter for planets because they can deliver impacts. Early in a system's history, impacts may bring water, organics, and heat. They may also reshape surfaces. On Earth, impacts are part of the deep story of geology and biology. Around other stars, belts of small bodies could influence planets in similar ways. A belt of asteroids is not empty space with a few rocks. It is a reservoir of history. It holds material that did not become planets, but still belongs to the system's architecture. Between planets, small stones keep orbiting. In their dust, a star system remembers what it did not finish. Planetary systems can be tilted and misaligned. In the solar system, most planets orbit the Sun in nearly the same plane and in the same direction. This reflects their birth inside a rotating disk. But some exoplanet systems show surprising misalignments. A planet's orbit may be tilted compared with the star's rotation. In extreme cases, a planet may even orbit backward relative to the star's spin. These misalignments can be measured through effects such as the Rossiter-McLaughlin effect. During a transit, a planet blocks part of the rotating star. One side of the star is moving slightly toward us, and the other side slightly away. The blocked light changes the measured stellar spectrum in a way that can reveal the angle between the planet's orbit and the star's rotation. Hot Jupiters are especially interesting in this area. Some have strongly tilted orbits. This suggests dynamic histories. A planet may have been scattered by other planets, influenced by a companion star, or moved through complex migration pathways before settling close to its star. A tilted orbit is a quiet clue. It tells scientists that the system may not have remained flat and simple. Gravity may have lifted, twisted, or rearranged the planet's path long ago. Planet formation begins in disks, but not every system keeps the disk's original calm geometry. Sometimes the orbit itself is the fossil. A planet's tilted path remembers ancient motion. Some planets may orbit stars that are not like the Sun at all. The Sun is a G-type star, yellow-white, middle-aged, and steady by human standards. Many exoplanets orbit stars very different from it. Some orbit red dwarfs, small and cool. Some orbit K-type orange stars. Some orbit F-type stars, brighter and hotter than the Sun. Some orbit A-type stars, even hotter and more massive. Some orbit stellar remnants like white dwarfs or pulsars. The kind of star matters deeply. A red dwarf's habitable zone is close in. A hot star's habitable zone is farther out. A massive bright star may live a shorter life, giving planets less time for long biological histories as known on Earth. A small red dwarf may live for trillions of years, but its close-in planets may face flares and tidal locking. The star's color changes the light reaching the planet. Photosynthesis, if it existed, might adapt to different wavelengths. Atmospheres absorb and scatter different kinds of light. Clouds, hazes, and surfaces may appear different under a red star than under a yellow one. A planet is always in conversation with its star. Its climate, chemistry, and long-term future depend on the light it receives and the history of that light. There is no single kind of sun for all worlds. Across the galaxy, planets turn beneath red, orange, yellow, white, and fading stars. Some exoplanets may be covered in ice. Far from a star, water and other volatile materials can freeze. A planet beyond the warmer regions of its system may hold ice on its surface, in its crust, or deep within its structure. Some icy worlds may resemble larger versions of moons in the outer solar system. Others may have thick atmospheres or internal oceans hidden beneath frozen shells. Ice is not always still. On Earth, glaciers flow. On icy moons, crusts can crack and shift. In the outer solar system, internal heat and tidal forces can keep oceans liquid beneath ice. Around other stars, similar processes may occur on planets or moons that receive little starlight. A frozen surface does not automatically mean a dead interior. Heat can come from radioactive decay, leftover formation energy, or tidal flexing. If a planet or moon is pulled by a nearby giant planet or star, the changing gravity can warm its interior. Beneath ice, water may remain liquid for long times. For exoplanets, such worlds are hard to study. An icy surface may be faint. A hidden ocean may leave little atmospheric signal. If the planet does not transit, even its size may be uncertain. Still, icy planets are part of the wider story. Habitability may not be limited to sunlit surfaces. Some environments may be buried, quiet and protected. A frozen world may look silent from above. Beneath its ice, warmth may keep a slower secret. Some exoplanets may be dry desert worlds. A habitable zone planet does not need to be ocean-covered. It may have very little water. It may be a desert world, with dry basins, rocky plains, dust, and only small reservoirs of ice or vapor. Such worlds could still have climates worth studying. A dry planet behaves differently from an ocean planet. Water is a strong climate regulator. Oceans store heat, move energy, and supply water vapor for clouds. Without large oceans, a planet may have wider temperature swings. Its clouds may be fewer. Its weather may be thinner or more dust-driven. Yet dryness can sometimes expand the inner edge of habitability in climate models. With less water vapor, there may be less greenhouse warming from water. A dry planet closer to its star might avoid the runaway greenhouse effect that would threaten a wetter world. The details depend on atmosphere, rotation, clouds, and surface reflectivity. This shows why habitability is not only about distance. A planet's inventory of water matters. Too little water may limit life as known on Earth. Too much water may create deep oceans with high-pressure ice and limited rock-water exchange. Between those extremes are many possible climates. A desert world in another system might be quiet, rusty, pale, dark, or bright with salt flats. Even dryness is not one story. It is another way a planet can balance beneath its star. Some planets may have deep global oceans with no continents. A water-rich planet may be covered entirely by ocean. If the ocean is very deep, pressure at the bottom may become enormous. Under such pressure, water can form high-pressure ice phases, even at warm temperatures. This ice would not float at the surface like ordinary ice. It could form between the ocean and the rocky mantle. This matters for habitability, because rock-water interaction is important on Earth. Ocean water reacts with minerals, circulates through seafloor systems, and participates in chemical cycles. If high-pressure ice separates an ocean from rock, some chemical exchanges may be reduced. The planet may still have water, but the environment may not work like Earth's oceans. A water world with no continents would also have a different carbon cycle. On Earth, weathering of rocks on land helps regulate carbon dioxide over long time. Without land, climate regulation may follow other pathways, or may be less stable. Still, water worlds are fascinating. Their surfaces might be endless ocean under strange skies. Their weather could be shaped by global evaporation, clouds, storms, and heat transport. Their appearance from space might be dark blue, bright with clouds, or hidden under haze. A planet can have more water than Earth, and still not be Earth-like. An ocean can be too deep to be familiar. Rings around exoplanets may exist, though they are difficult to detect. Saturn's rings are one of the most beautiful sights in the solar system. They are made mostly of ice particles, from tiny grains to larger chunks, all orbiting Saturn in a thin, bright disk. Other giant planets have rings too, though fainter. It is natural to expect that some exoplanets may also have rings. A ringed planet passing in front of its star could create a transit shape different from a simple round planet. The rings might cause extra dimming before and after the planet itself crosses. They might make the planet appear larger or create asymmetries in the light curve. Detecting rings is very challenging. The signal must be separated from star spots, moons, other planets, and instrumental effects. Ring orientation matters too. A ring system seen edge-on may be hard to detect. One seen at a wider angle may create a stronger signal. There have been candidates and discussions, but confirmed exo-rings remain difficult. The idea remains a quiet frontier. If found clearly, rings could reveal information about moons, collisions, tidal forces, and the history of a planetary system. Rings are made from small pieces, but together they create grand shapes. Around some distant giant, a thin disk of ice and dust may be circling unseen. Planets can influence the dust and light around their stars. Even when a planet is not directly detected, it may shape its environment. A giant planet can carve a gap in a disk. It can shepherd dust into rings. It can scatter comets. It can stir asteroid belts and increase collisions. It can create patterns that telescopes see in infrared or scattered light. This is why disks are so valuable. They are not merely background material. They are responsive structures. Their gaps, spirals, clumps, warps, and edges can all suggest gravitational sculpting. Young planets embedded in disks can create clear signatures. Older planets may shape debris belts more subtly. A planet too faint to image may still reveal itself through the architecture of dust. The same is true in the solar system. Jupiter shapes the asteroid belt. Neptune shapes parts of the Kuiper belt. Planets create resonances, clear regions, and guide small bodies into families of orbits. Around other stars, similar gravitational fingerprints can be seen from far away. A ring of dust may be offset. A belt may have a sharp edge. A disk may be warped. Behind these patterns, a planet may be moving quietly. A world does not need to shine to show its presence. Sometimes it is seen in the paths of smaller things. The search for Earth-like planets is really a search for Earth-context planets. A planet the size of Earth is not enough. Venus is close to Earth in size, but its atmosphere and surface are profoundly different. Mars is smaller, colder, and thinner-aired. Earth is Earth because many factors work together. An Earth-context planet would need more than radius. It would need a suitable orbit. It would need a star with a helpful long-term history. It would need an atmosphere that supports stable temperatures. It might need water, geology, climate cycles, and time. If life is the question, it also needs chemistry capable of becoming biology. This is why scientists speak carefully. Earth size does not mean Earth-like. Habitable zone does not mean inhabited. Water vapor does not mean oceans. Oxygen does not automatically mean life. Every clue must be placed into a broader setting. This careful language does not reduce wonder. It deepens it. It shows how many things make a planet what it is. A world is not one measurement. It is a system of relationships. When future telescopes find small planets around nearby stars, the goal will be context. Size, mass, orbit, atmosphere, star, age, and climate must come together. A second Earth, if one exists, will not be recognized by one number. It will emerge slowly, as a whole world. The silence of exoplanets is not emptiness. No voices arrive from these planets. No oceans are heard. No winds are felt. No sunrise is watched from their surfaces. Most remain points in data, tiny changes in light, or movements of stars too small for the eye to notice. Yet silence is not absence. The planets are moving whether or not they are seen. Their atmospheres, if they have them, are turning through weather. Their interiors are cooling. Their stars are shining. Their orbits are repeating. Their moons, if they have moons, are circling. Their dust is drifting. Astronomy often begins with silence. It notices that silence is patterned. A star dims at regular intervals. A spectrum has missing colors. A wobble repeats. A gravitational lens brightens and fades. The pattern becomes evidence. The evidence becomes a planet. There is comfort in this. The universe does not need to be loud to be full. Some of its richest truths arrive quietly. They wait in small signals, repeated with patience. The night sky may look still, but beyond the stillness, worlds are turning everywhere. Exoplanets turn the Milky Way into a place of hidden weather. Before exoplanets were known, weather seemed mostly local. Earth had rain, wind, clouds, snow, and storms. Other solar system worlds added more examples. Dust storms on Mars, sulfuric acid clouds on Venus, ammonia storms on Jupiter, methane rain on Titan, supersonic winds on Neptune. Exoplanets expand that weather map beyond the Sun. On some hot Jupiters, winds may carry heat around permanent day and night sides. On ultra-hot worlds, metals may vaporize and condense. On lava planets, minerals may move between surface and sky. On puffy giants, clouds and haze may spread through enormous atmospheres. On temperate rocky worlds, weather may be quieter if air and water are present. Weather is matter responding to energy. Change the star, the orbit, the atmosphere, the rotation, and the ingredients, and weather changes too. Rain is not always water. Clouds are not always white. Winds are not always driven by familiar continents and oceans. This variety is not chaotic. It is physics, chemistry, and motion expressed under different conditions. Each planet is an experiment running for millions or billions of years. The galaxy is not only full of worlds, it is full of skies, each one shaped by its own light. Exoplanets make the solar system feel like one chapter in a much larger book. The solar system remains deeply beautiful. Mercury's metal-rich body, Venus's clouded brightness, Earth's oceans, Mars's dry valleys, Jupiter's storms, Saturn's rings, Uranus's tilt, Neptune's winds, Pluto's icy plains. The moons, asteroids, comets, and dust all form a rich and familiar neighborhood. Exoplanets do not replace that story. They place it into a wider library. They show that hot Jupiters can orbit in days. Super-Earths can fill the size gap absent here. Mini-Neptunes can be common. Compact resonant chains can gather near small stars. Giant planets can glow young and wide. Planets can orbit two stars, white dwarfs and pulsars. Some may wander alone. The solar system becomes one arrangement among many. It is neither the only model nor an insignificant accident. It is a local example, close enough to study with spacecraft and rich enough to teach the first lessons. Every distant discovery returns something to home. It helps ask why Jupiter stayed far out, why Earth kept oceans, why Venus changed, why Mars cooled, why the solar system lacks close-in super-Earths, why our planets settled into their present architecture. The faraway worlds make the nearby worlds more meaningful. By studying others, the solar system becomes newly strange and newly precious. The search will continue because every answer opens a gentler question. At first, the question was whether planets existed beyond the sun. Then the answer came, yes. The next question was whether they were common. Again, the answer grew clearer, yes, very likely. Then came the questions of size, mass, orbit, atmosphere, climate, chemistry, and possible habitability. Each stage leads onward. A planet is found. What is it made of? Its atmosphere is detected. What gases are there? A gas appears. What produced it? The planet lies in the habitable zone. Does it have air? Does it have water? Has it kept stable conditions? Is there geology? Is there life? If no sign appears, what does that absence mean? Science does not empty wonder by answering. It gives wonder more detail. It replaces vague mystery with deeper mystery. It turns a dark point into a star into a system into worlds, and worlds into climates, histories, and questions. The search for exoplanets will continue across generations. New telescopes will look. Old data will be revisited. Instruments will improve. Some worlds now hidden will become measurable. Some familiar planets will become better understood. The universe is generous with questions. Around every answer, new orbits begin. The most relaxing fact about exoplanets may be that they are simply there. They do not wait for human discovery in order to exist. They do not need names, catalogs, headlines, or diagrams. Long before telescopes found them, they were already moving. Long before Earth formed, some planets may have circled older stars. Long after tonight, distant worlds will continue their paths. Some are hot, some are cold, some are giant, some are small, some are young and glowing, some are old and dark, some keep close company with their stars, some move in wide silence, some may have skies, some may have no air at all, some may be rocky, icy, oceanic, gaseous, hazy, ringed, tilted, or alone. They are not ideas, they are places, even when no one can visit them. They are part of the ordinary richness of the galaxy. Their existence makes the night sky feel softer and fuller. When a person looks up at the stars, the eyes see lights, but the mind can now know that around many of those lights, worlds may be turning. No sound crosses the distance, only the quiet certainty that the dark is filled with planets. And now, this long journey beyond the sun can begin to settle. The universe is not only large, it is patient. It makes stars from clouds, disks from leftover material, and planets from dust that gathers one grain at a time. It places giant worlds close to their suns, Small rocky planets in dim red light, ocean candidates under distant skies, and wandering worlds beneath the wide glow of the galaxy. You do not need to travel any farther tonight. Let the names soften now. Let Kepler, TS, Webb, TRAPPIST-1, Proxima Centauri, 51 Pegasi, and all the faraway worlds become quiet points of light in the mind. Let their orbits slow into a calm circle. Let their stars grow gentle and small. Let the great distances become peaceful instead of vast. You have drifted past hot Jupiters and super-Earths, through shadows, spectra, wobbles, disks, dust, clouds, atmospheres, and soft questions about life. You have followed planets that rain iron, planets that glow with molten stone, planets that may hold oceans, and planets that move unseen around the nearest stars. For now, there is nothing more to solve. Let the science rest. Let the stars rest. Let the room around you become quiet and easy. Your breathing can slow at its own pace. Your thoughts can loosen their hold. The faraway planets will keep moving without effort, and the night will keep them gently. And if you are still awake and would like to keep drifting, another quiet journey is waiting for you on screen. If these calm nights bring you a little peace, you are always welcome to return and wander gently through science again, one drifting mind at a time. Sleep well, and good night.